Okay, we're going to go ahead and get started this morning. So welcome to day 3 or day 2, depending if you came the first day. We're going to have our final tutorial session this morning. Helen Kershaw is going to talk to us about Git and GitHub and automated testing. Thank you, Helen.
All right. Morning, everyone. Beginning, all right? Cool. I'm Helen. I'm a programmer with the Data Simulation Research Group here, NSF. I'm not going to talk about that today. I'm going to talk about Git and GitHub. I realize this is going to be quite a mixed audience of experts and beginners and all sorts. So feel free to jump in with tips, questions, objections. And I'm English, so I talk funny. So I'm going to do my best to go slow and understandable, but if you can't tell what I'm saying, stop me, and I'll do my best. Ooh, here we go. So I guess why should you care about version control, which is like how things change through time and why? You can recover previous versions. Multiple people can work on the same project. You can tag a version of your code that was used with a particular paper. For this group, it allows you to test versions of the code. And it's just a great skill for everyone. I'd say anything you can edit can benefit from version control. The caveat here with Git is it doesn't do binary files very well. So if you're going to try and save differences in netcdf files, it's not the tool for you. I guess this is just some motivation about how good it is. This is a fairly old slide now. 1,500, 1,600 developers, 1,400 companies have contributed to the Linux kernel. So Git scales. It allows you to do enormous things, and the world runs on Linux, right? So the goals for this talk, which is quite short and with a lot of material, so we'll do our best, is to understand Git basics, get a good mental model of Git, learn a little bit about GitHub and collaborating from like the open source point of view. We'll probably do actions next. So that's like the automated testing. You might have seen, forgotten the guy's name, the guy who did the Met Plus talk yesterday with those extremes. Yeah, so a little bit simpler than that, but on the way. Yeah, and then if we time, we'll get into creating and fixing conflicts. So what is Git? So this is the original commit of Git, which you can look up on GitHub. It's a random 3-letter word, kind of sounds like get. This was back in the day when you could say things like stupid. Global Information Tracker, which is a really nice backronym, and then a goddamn idiotic truckload of stuff when it breaks, right? And guaranteed you will feel all of those things when you use Git. Yeah, it's actually created by Linus Torvalds, who wrote the Linux kernel. Git's actually a mild English swear word. It means like idiot, like, so they're both named after him. Yes, so it's version control. So it's tracking changes in files and supports collaboration. And really, like, I'm going to talk about commits a lot, and that's like the unit of change. So it's a snapshot of your project at a specific point in time. This is one of Alison's commits. Alison, famous for winning a Gordon Bell Prize. So the nice thing about, and we'll go into this like this thing here is this hash is the commit. So it's what changed, and a little message about why. That's all we're doing over and over and over again. Yeah, and so like I said, I like to think about it as a way of communicating change. This is what I've changed, is what I've changed. I've bundled it up for you. You can take it, apply it to your stuff. You can do the inverse of it if you want to undo it. And like for this group where you're concerned about rigor and reproducibility, it's traceable, right? You can tie results of a code to a specific commit. You can reproduce. I mean, I feel like you never exactly run the same code, which is, when we get into push into GitHub, we'll talk about that. But yeah, traceability, reproducibility. There's a massive assumption here that like your commits are atomic. So that's using it as a skill, right? When everyone starts out, they commit half of this work, put it in one commit. Yeah, is everyone familiar with the word atomic? Because I'm assuming everyone is computer science. Anyone not familiar? Anyone want to shout out what they think it means? I don't have chocolates to give to people, but how do you define atomic in terms of Git then? Best answer. Yeah, and like, I want to say like encapsulate, like one change, total change, does everything.
I feel like people talk about it. The normal way you hear about atomic stuff is with like databases. So like if I give $10 to Allison and we don't do that atomically, there's $20 in existence at once, right? There's that kind of thinking. Anyway, Git concepts. A repository, that's where you store your changes, and a remote. So that's a repository that is on someone else's machine. So it might be GitHub. So the nature of Git is that like all the repositories are true. So they're all equal. In practice, we don't work like that. Normally we have like one truth, like the Dart repo on GitHub is the truth, or the CSM repo is the truth. But yeah, so how it does its magic, there's a hidden directory Git when you make a Git repo in your project. So that's where Git stores all its information, the metadata, the object database, all the changes, everything on your local machine. And you always follow this pattern, which I think is not that intuitive, right? There's always this like two-stage add and commit. So edit your files with your science or your amazing rigorous tests. That's your problem, not mine. Add, so you change it, like, oh, this is what I'm thinking about adding to the commit. And then you commit and take the snapshot. And that commit is what you communicate in of what you've changed. And the commit's what's saved in the Git repository. And then the other thing we're going to talk about is GitHub. So GitHub's owned by Microsoft. People have opinions on that. They can discuss them later. But yeah, so it's a place to store your repos online, which they will mine and train AI with. And it's got some social media aspects as well. I love GitHub because I'm really nosy and I love to look at people's code. Like you can look at the Apollo guidance system on GitHub if you want. I think you can run it, but you can have a look at what the code does. You can see what people do. This is Brigitte, who is one of the maintainers of AstroPi. So you can stalk people, see if they work weekends, have a look at how they think. Yeah, have a look at what they do. It's super cool if you like me and you just like to nosy at code. But yeah, go for it.
How much is Microsoft allowed to mine that and get any info out of it versus public even? Do you know that? I never looked at the licensing.
I think it's all mine.
Okay.
So like, yeah, so I think
GitHub is amazing, and I don't know, they've redone all their search and Rust, so it's crazy fast. You can search like the entirety of GitHub repos. And then I don't know if you've ever, like we sometimes get strange emails about people working on forks of Dart. So they'll comment on a commit and everything underneath is linked in GitHub. So I am not sure if it's private, that it's genuinely hidden. But what do I know, right? Email Microsoft, they won't tell you. But yeah, like it's not the only thing. Bitbucket is another one. It's really nice, and people like host their own servers. Yeah, and then all I'm doing is loading you up with terminology, but pull and push. So that is to remote repositories. So you've done your commit, you've got your change, this change, and this. You want to shove it to someone else so they can use it. It's a push. You want to grab someone else's changes. It's a pull. I don't know how amazing that picture is, but yeah, local machine to GitHub. That's generally what we're going to talk about today with push and pull. Everyone here probably already has set up Git, but we'll go over it just in case people haven't. We'll set up the name and email you want to use and the editor you want to write commit messages with. I like to go over this, especially we get this with students a lot, where they forget to set this and they'll commit from Duratio. So the email will be duratio@UCAR. And I guess this goes back to public but private. Your email is going to be public if you do this. So if you don't want your email public, like I don't care, it's my work email, like email me. But yeah, you can set up a no reply email address. And that's like the social media aspect. That's going to link your work to GitHub for when you want a new job. But yeah, and we can take a look at my Git config. Yeah, so this is me. I just have my regular email. I have a bunch of stuff because my job is looking at other people's code. Yours might not have so many directories on there. I always think this is a mistake to include the slides because this is a bunch of people who don't know how to use VI, OpenVI. but you can use whatever editor you want. Doesn't mean you have to edit your code with it. It just means when you open the commit message, right, that's the editor it's going to use. Just did this for me. You can see what your settings are. You can have global settings. So like everything on one machine is going to use the same settings. You can set by repo. Files you should probably have in every repo. A README, that's like the front page on GitHub, a git ignore file, and a license. A README is like the front page. I'm nosy, so I like to look at other people's stuff. I was trying to find a really bad README, and I found this issue, which I love. README is absurdly large and unintuitive. So yeah, so there's really good ones, really bad ones. Git ignore is really important. So this is essentially anything you don't want to track. So things like binaries, you don't want to accidentally add things. So you can wildcard it. You can put specific programs in. It just saves you add in a bunch of stuff you don't want to add, and then you're unable to push it to GitHub. You definitely don't want to add binaries, log files, temporary files. This is a big one, sensitive information. So like if you committed, I don't know, your social security number or your API key or your GitHub unencrypted token or whatever, or large files. For those of you who use like Python environments, you notice they never show up in git status because when you create them, they already have a git ignore in. So if you want to play tricks with people, add .gitignore files to the directories. License, that's way out of scope. This is a legal problem. It's good to check it out. If you want some juicy gossip, I would chat to the CSM developers about various license choices through history. It's a good half-hour chat. All right, if you want to follow along, do, like I said, maybe I forgot to mention that. I put it in the chat. Everything's in this repo with a link to the slides. And hopefully I put a link to the slides in the chat as well. But yeah, how are we, should I do create repository or should I move along? I don't know what. Oh, we'll do it. Yeah, so I'll just do it on, I'm on Durisha. We'll make my first auto repo. Do GitNet. Yeah, this is many discussions on this. So typically people don't call branches master anymore. Git does that by default. Yeah, so, and then, oh yeah, I forgot to mention this. I have it set up on my prompt to tell me which branch I'm on when I'm in a Git repo. I would highly recommend if you don't do this, set this up. You can just add it to your profile. You can chat to me if you want some tips on how to do that. Yeah, and it just creates this Git directory. And so that is all Git's information about what you've done, and what it's doing. You never have to look at that. But yeah, that's the repo. And everything outside that is your worker tree. There's a lot of tree branch terminology in Git. Most useful command I think in Git is git status, and we haven't done anything. Very useful when you're looking at other people's code, debugging when they say they haven't changed anything, or they haven't edited anything, or they haven't done like, yeah, I guess we'll just do a git ignore, just fix. And then it's two-stage, so git add. So we have this. And git commit this empty file. Empty git. So we've made our first baby commit ever. So take a look at the log. We only have one commit. This giant thing is the hash. So that's like the unique value of the commit. That's how you communicate about the commit. Git log one will log one line will do, but it's not gonna be very exciting because it's one commit. Oh, and I can't spell. This is, I guess, a a best practice, or, I mean, this is something when you work with your group, how you want to do these. Lots of people like the one line and then a bigger description, because that's easier to, you can tell I've taught this to a lot of nerds, that's why. And then, so it makes the one line log easy to read and more detail. There's all sorts of tools. Commitison is quite nice. I don't know if people have used that, where it forces you to say if something's a feature, say if something's a bug fix. But it depends, I don't know, it depends how tough you want to be on the people you work with. Because the danger of that is they just won't commit. So that's, I don't know, it's a technical solution to a social problem, right? Yeah, go for it. Yeah, that's perfect. I think I just remembered that's John, right? Yeah, John. So yeah, so that's really nice. And that way people can link to the issue on GitHub. GitHub's super nice about click on the issue, read the issue, read the problem. This is me going through the GitHub lecture as I was building it. Probably should have put that DS store in a gitignore file. It's just a temporary file. I would say, so no one reads error messages. I don't know if you, like, if you worked in support, have you ever got like an email with the exact error message and what to do? And someone goes, I don't know what to do. And then you copy and paste it back and they go, oh, great. So like something happens to people's brains, like when something goes wrong. So Git status, it is really useful. It will tell you, oh, these are the things you can do and this is what you should do. And so if you get in the habit of reading that, when you panic, you'll understand it. Apologies if anyone's red-green colorblind. I think that's the default for Git. So these are actually different colors once you've added. Yeah, it's log, we've already done log. Yeah, so undoing changes. So there's always like a billion ways to do things in Git. So I'm just going to talk about a couple. I like to practice. So we have a practice repo with that is just full of nonsense. It's got like cat pictures, lists of animals. It's just we do it especially with students, so they can just we can break things and unbreak them in like zero consequence. So I highly recommend just playing with Git, and it's really fun to break things when it's not yours. So yeah, like Git stats is going to give you instructions for just unstaging it. That's easy. This I always find quite useful if you've done a bunch of stuff and you're like, oh, this is garbage. I just want to check out an older version of the file. So again, this hash, this is how it's going to identify a commit. These are the two big ones, reset and revert. So one is going to rewrite history, and one is going to just add to the history. So reset, rewrites history. So this is, you might break other people's stuff. But it's really good if you're cleaning up your own local history. So what I see a lot of people do is they'll commit something they don't want to a branch, panic, and just blast the branch, delete the branch. But you can change history locally, no problem. Just be aware, if you force push this up, this is going to affect other people's work. Revert just takes the commit, does the inverse, and applies it. So all the stuff you didn't mean to do, you undo it, but you could get back any stage. So I did this lecture a couple of weeks ago to a bunch of oceanography modelers, like student modelers, and they just loved reset. Like all they want to do is the dangerous stuff. So like, it's good. Yeah, again, this is something I would definitely play with. So working with remotes. Yeah, so it's the repo but somewhere else. So you can have multiple remotes. The default remote is called the origin, truth, as we tend to think about it. So yeah, in your little Git directory, all your work on your local machine, the original repo, which is on GitHub, the fork, that'll be the origin, and the pull request. So I've already introduced a bunch more terminology, fork versus clone. So clone is like Dolly the sheep, it's a copy. So you copy it from GitHub to your machine. Multiple people can work on the same if they have permission to write to GitHub. Now, forking is like a GitHub concept versus a Git concept. So forking is creating your own copy. So it's a copy of the entire repo on GitHub. So you can push to that without affecting the original. fork is just, it's like a GitHub way of saying these two repositories are linked. You can tell I taught a bunch of oceanographers. So yeah, let's look at Crocodile has MOM6, which is a fork of NCAR MOM6, which is a fork of GFDL MOM6 as ocean models. So this adds up to a lot of code pretty quickly. So this is all the forks of MOM6. They all have multiple branches as well. We keep going and we keep going and we keep going. So this is why I have gray hair, because I work in open source. But yeah, so it's a lot of code, and there's really like the motivation for things like you guys like testing and rigor and automating and just dealing with the enormous volume of possible changes and who's working on the code. This is because I like to be nosy. You can have, this is a really nice tool, OSS Insight. You can just type in a repo and it tells you who's starring it, where they are, who's telling you there's a bunch of problems, who's creating the pull requests. So super cool if you do have an open source project. Really nice for metrics. Let's kind of clone a repo. You can pick this one. This takes a little while to to download. I have a tiny repo that we're going to build some actions on. So I'll just download it onto Duratio, clone it onto Duratio. Git clone, which is like the first time you copy. Oh, let's do it on GitHub. So this green button, copy it. And so it does its thing. So we'll go in little repo, look at the log. This is me talking to myself. But yeah, so that's our little repo. So you can do that with anything, have a nosy on your machine, run stuff. Yeah, so let's check out an earlier version. I'm going to trust that this is an actual commit. Check out. Sorry, let's make this bigger so people can read. Hello. So I've checked out an individual commit. Check out branch. So any version, go back in time. So, all right, quiz. What's the difference between a commit and a branch if you check out a commit versus checking out a branch? Yeah, so commit's like frozen in time, whereas a branch is it's like you can change it, move through time, add commits. So you might see sometimes like, I don't know if you guys work with CSM. So they typically force you to commit out check out a given tag or a given commit. And so you'll see like, oh, I'm in a detached head. And that's because they want you to use this. And they want you to think about it if you're going to make changes. Yeah, branches are a way to allow you to work on new features without affecting the main branch until you're ready to make your changes back in main. So this is the bit to get like a mental model of. So this amazing picture. Circles are commits through time. So this is main, but you want to do something cool and different. So you branch off, you do your work. Main can continue. You can work in sort of isolation. So git branch. I only have one branch on this repo. Git branch -a will show you all your local branches. Again, it's red-green, which is kind of a pain, and all the remote branches. So I only have one remote. I have origin, and the star, the asterisk, is the branch you're on. This is how I tend to think about it, and I think this is probably what you care most about with rigor and reproducibility and like how you give people code. So there's different ways you can bring your branch back into main. Rebase as though it happened afterwards, which is a lie, right? But it's better in some ways. Merge, like a regular merge, puts them in genuinely when they happened in time. This is what we do in Dart because we have a lot of people working on the code, doing their own stuff, getting changes. Yeah, we keep it, I would say, like simple in terms of pulling, pushing, merging. But yeah, it means our history is quite intertwined. So that might not be what you want for your project. Every time you bring a new feature in, you want to go like, boom, this is a new feature. And so your history is really nice and linear. Yeah, that is something to like chat about with your fellow developers. And then squash, which I really dig. So that collapses all the commits as though they were one. So your history's gone essentially. But yeah, so those, I don't know, that is something to think about, and I guess have a mental model of how you want to get your changes in and give it to other people. Make sense? No? Yeah.
Force like anything to come in as a squashed commit or not. Like, I'm just curious, what do you do that, or do you?
So we do not do that.
Okay.
So we are like,
Yeah, it's a, no, we don't do that at all. So we have like a bazillion merge commits. Yeah, go for it. Yeah.
It's more so that gives you a very long commit message, which is all the commit messages of everything that occurred on that feature branch or the bug fix branch. So you can see that, but we find it's easier to like keep track of when something breaks to go back it out. But why? So you guys use merges?
yeah, we do. And I don't know if I can really
Justify it with a good reason that we've done it, and then we'll still do it.
Add my opinion. I like merges, but along with the git log first parent. So first
Yeah.
parent will just give you like a quick summary then of all the merge commits that have happened to your main branch essentially.
And we have a lot of long-lived branches as well. So we do a lot of merges from main to feature branches. Which I know some people do not. I mean, some people don't use branches, right? Like if your testing is extremely good, you can just commit to main, right? I believe that is what part of extreme programming, which sounds cooler than it is. But yeah, definitely like this. So that I think if you're interested in nosy, like have a look at the data history and go, like, oh, well, is this helpful? All these mergers, is it not helpful? Have a look at the, the met plus. Oh, is this nicer because it's linear? Is it nice? Like have a look and like which is better as a user and a developer.
You don't want people to feel like their commits are being scrutinized by others. You know what I mean?
Even
So
if
if you squash it, but if you squash it, then it's like, hey, I feel good about this result, even though I went all sorts of ways to get there.
Now, if I merge some changes using rebase into the main branch, do I need to get rid of that feature branch that I've rebased, or can I keep working on it? Because now there's a discrepancy between that feature branch history and the main.
That's a really good question. I mean, really good question.
I'm paranoid, so I would get rid of it once I'd rebased it, because I think that's the point of rebasing. Now it's in the main, it's there. Yeah, rather than continually, yeah, go for it.
Hydro project, and we require linear history. We don't require squashing, but we require linear history. And so contributors will commit their branch with a rebase and then be all confused as to why they can't keep using it because it's all completely out of sync. So that's kind of a common help desk thing. But yeah, we don't require squashing, but our philosophy is if you submit a PR that has a ton of commits, especially like daily check-in, squash that. So like at least squash to like sort of atomic pieces. Like if your PR does two things, have two commits so that we can undo one if needed. And ideally it should probably have been two PRs, but life gets in the way, right?
So for Alpha's question, when you have a branch and you rebase it, in the branch, you usually have, whenever, let's say you make some changes, you can keep the separate branch. And when you're trying to commit, that's when the GitHub says that the main branch is so and so many times ahead of what you're doing. So you have to basically, I don't want to say clone, but you have to make it exactly same to what you're in the main branch. So whenever you are rebasing again, you don't mess up what you
Yeah, that's, I guess I think you kind of hit the nail on the head of what I think trips people up with Git a lot is that like
you have a repo here and you're like, oh, it's up to date, it's not up to date, and the GitHub, someone else has put a bunch up here. And yeah, so keeping in sync, and then rebase makes you're never gonna be in sync again. Yeah. Did I hit what you were talking about there? Thanks. So forks, clones, and branches. Clone, copy. Branch, a separate line of development. Yeah, go for it.
There's a way to interactive rebase
Yeah.
with which you can also squash selected commits.
Yeah, that I would say is really nice. I definitely play with that. So I use that a lot because I like to overcommit and then tidy up.
Scientists that interactive rebase, we've learned the hard way that can cause problems when you.
Yeah, all the problems are social, right?
Yeah.
We have technicals with like, what do you do and how?
Don't
Yeah.
know which one is yours sometimes, for me at least, and then you have to keep. It takes some time to.
Yeah, and I think this is, I mean, it depends how dispersed your group is, right? Like some group, they're all over the world, different times, different things, slightly different projects. But how, like, I think the people you work with, like having like regular chats about like, oh, this is how we're going to do stuff, or like, oh, we're going to learn squash it, but like, and at least, I mean, you have to pick a pattern for the way you're going to do things. Fork, GitHub. Maybe we'll skip that. Oh, maybe we'll just show it. Yeah, so if you have Git remote, oh, I don't have a remote, I've already, anyway, you can see which remotes you're attached to. Right, bonus question, what's the difference between fetch and pull? Yeah, go on for a moment.
Pull will apply the changes, like pull is a fetch and a merge, like fetch gets it from the remote, but doesn't do anything locally.
Cool. All right. So open source, which is fun stuff. So get involved. I don't know about you, I feel like our open source is under tested. So if people contribute tests, that would make me extremely happy. But yeah, issues, your code sucks, this is why. It's always good. Reviews, pull requests, even just starring it helps us out. So this is the kind of simple picture. Really, it's hundreds, maybe thousands of people, and look how happy they are contributing to open source. But all these things can break, like, yeah, all these things like places where like people can introduce breaking changes, or you can break all these people's science, which is fun. I mean, not fun, but what's the opposite of fun? But yeah, you don't want to break people's stuff on Friday night. So like you're always working with other people's code, right? That's what remote is. And whether that's other people in a team, so they're just pushing and they have write permission, whether it's someone who doesn't have write permission, do you take the code? You can review it, like, do we even want this? What we're going to do with it? And you can test it. And so you want to welcome contributions, right? So you want to be super welcoming and lower barriers to entry, but you also want to have a bunch of barriers. So like those are the things you're trying to balance, right? Branch protection rules, which I think has already been mentioned. Yeah, we don't have that many on Dart, but I guess I'll show you so you can set them up on GitHub. So you have main protected, pull requests, approvals. We actually don't require one review because we hardly have any people. Status checks are our tests that have to pass. Just because he's in the room. We have a locked branch because my boss keeps committing to a branch that is dead. Sorry, Jeff. But yeah, like, so you can control what people do on GitHub, and you should. So test must pass, or documentation must build, or whatever. It has to do this before we'll accept it. So automated testing. That's kind of what we're here to talk about. So GitHub Actions is nice. I feel like it's down a lot. I feel like GitHub has a lot of downtime. But it's free for open source projects, and it allows you to automatically run your tests or your documentation builds when you push changes to GitHub. So you saw a really nice example from the Met Plus people yesterday. Super complicated, not super complicated, complicated enough for the workflow, right? You can have scheduled tests, which is what we would do. That's traditionally like cron, like running cron jobs under ratio, nightly cron jobs. Go for a bunch more terminology. Workflow, you can link to the enormous GitHub documentation if you want. So it's a configurable process that's going to run something when you trigger it. It's all YAML, just like white space sensitive. And they're always in .github hidden directory workflows. So if you want to look at what people do, have a look in there. Actions is like a predefined reusable bit of code. I always get confused because it's called GitHub Actions, but the workflows are the actions, and actions aren't actions. Anyway, it reduces repetition. Trigger is when you want it to run, so on a schedule. So if you do things like, we have someone who grabs ocean data and they build a database that they give to people, so that you want to run every so often and get new data, or you might want to test something's still working, ingesting it every night on a push to a branch or on a pull request. And the runner is like where you want it to run. So that's the machine. So GitHub has a bunch of runners. They're not crazy big in terms of like memory and cores, but they're pretty good. And you can also self-host your runners. So we have interns do this all the time because you can actually set up a runner under ratio and have like a pull request run as you under ratio. You do not want to do that, right? The duration, HPC support will get annoyed, but you can do that. NCAR's just spun up their own cloud. So I don't know if anyone is using that already. So running GitHub Actions on NCAR Cloud, where the ratios, Glade is mounted as read-only. So if anyone would like to chat about that, I'd be super interested. They're already doing it. Yeah, and a job is a set of things that's going to happen. Matrix is really useful. Metrics and dependent jobs. This is really similar to like if you submit HPC jobs, like a job array, metric, same thing. I'm going to look at one. So this is one we have for Dart. It's just on dispatch because it tries to find everything possible and build it, which you don't want to do without trusting what people are giving you. So we have a look, then we run it. We find everything possible it can build, which for Dart is like 96 programs, and then it runs them all. So maybe let's take a look at a run. Look at one that fails because it's more interesting. So yeah, it's a setup job, and then all these other build jobs are dependent on setup. So once that's finished, just tries to build all these things. So that's where the matrix comes in. They all run in parallel. Didn't run these parallel, it'd probably be like an hour, which is too long to wait for any test. And I feel sorry. Is it like people who do like hardware and they have to go and fabricate it and then test it? Like, yeah, more patience than me. But yeah, they're nice. It shows you the log. It shows you where it failed, what happened. You can take a look, and it emails you to tell you you suck. You have to do something about it. So things to think about is how you test an action. So like you probably don't want to do a bunch of commits to YAML file on your repo that is going out to people. So VS Code has some like tools for testing actions. I was just make another repo, upload actions. Containers for dependencies. So John talked about that, especially if you're giving them out, you do want to worry about vulnerabilities in them, but they're really nice. So we have a bunch of dependencies, not a bunch. Some of our, like we work with a bunch of observations and they have like all sorts of library dependencies. And so other people don't care about those. So they don't regularly test that. So we just have a container with all the various libraries. Yeah, go for it.
I'm not a Git expert by any means. We have a binary instrumentation tool that runs on GPUs. Once we wanted to set up a GitHub Actions, my postdoc looked into it and said, this is not that easy. And I can talk offline, but suppose I want anybody who commits a new CUDA kernel to have the advantage of running GitHub Action, our tool, and assume they have a GPU on their machine,
Yes.
I don't know how one sets up these things, so maybe I can ask later, yeah.
Cool.
Is it a straightforward thing or is it
So,
hard?
so the example I'm gonna show is really simple. It's gonna set Python,
like a Python test. Yeah, like GitHub runners, they do actually have GPU. I believe this is true. Someone can correct me. And I would say if it's your tool, you can containerize it. And so you can pull like the Dart dependency just pulls from Docker. It pulls the Dart container from Docker. That might be the simplest. I don't know if you want a bunch of various GPUs to test on. Then I'd maybe look at the self-hosted. But yeah, what do you want to automate? Tests, documentation builds, deployments. Simple example and a not so simple example. I just picked X-ray because I think GPAC has done a bunch of stuff on X-ray. So you can see what they do. They just run on Ubuntu. They use Matrix. They use all various Python versions that they support. Oh, go away. They're doing set up Micromember, test the install with that. Oh, they're actually doing the hypothesis, which Deepak talked about, and then they run their tests. Yeah, so that it's not so simple, but not crazy complicated. And then we'll set one up for little repo. So this is where, so I kind of get what you're saying. So like the documentation and the examples, this is going to look easy, but for like your actual problem, more complicated. But we'll go through it. So this is the little repo that we downloaded earlier. So what it does, it says hello, and we have some tests. We have a test that passes and a test that fails. I'd always recommend having a fail whenever you set up an action, so you know you can catch a failure. So let's set up an action. So there's always a bunch of suggestions. We are just going to do a Python and test the Python application. We'll just push them in, fine. Permissions, so this is where you do want to be conscious of security. So I actually wrote a tutorial all about code review, and I have an action on that resets the tutorial. So it full on resets the repository, closes all the pull requests, closes all the issues, wipes the history, goes back to the beginning. So like someone could write that for your repo and submit it as a pull request. So yeah, so it is another level of like things you want to be aware about. What is running, what permission this action is going to do, what it's capable of, and keep it as little as possible. So this is read. I'm just going to check out, set up Python, lint, and then run PyTest. So we're like, cool, that'll work for us. Go away, Copilot. Sure. And since we've committed to min, I think that should just run. Yeah, so because we committed the action to min and the trigger is run when someone commits to min, it's running or it's getting set up. So you get very familiar with these when you use actions, go through the steps. Oh, it's failed, it's going to send me an email saying you fail at life, Helen. There, and tells you what happens. So like, oh, I don't know if you did Manisha's tutorial on PyTest. And so if you've got you work with Python or I don't know, say you work with CMake and you use CMake test and all that stuff, you run it in your action, same result. There's a bunch of utilities that are really helpful. So linters, I really like black because it's like no questions asked. It's black, this is what we're linting because I've spent too much of my life chatting about spaces versus tabs. Yeah, you can lint stuff. Code coverage gives you nice, pretty pictures of, I think this is from X-ray. You can have a nosy at, oh, this changed, what's actually covered by the tests, what isn't covered. Read the docs. I feel someone else is talking about read the docs and get pages. So there's a bunch more you can automate. I think I'm pretty much out of time. So there's all sorts of stuff about conflicts, which feel free to chat to me about or shoot me an email about, but I guess probably gonna stop there. Take any questions, comments, tips people have. security nightmares from actions, whatever people want to have.
Yeah, we have 5 minutes if anyone wants to ask.
Yeah,
Is there a way that you can tie an action to, block pull requests?
yeah. You know, Black the Winter.
I'm sorry?
Oh, maybe I misheard the question.
So imagine that I've got an action that's gonna run tests.
Yep.
When someone, puts up a pull request, and if the tests fail, I don't want to allow the pull request to get merged.
Yeah, so so the status check, if you set it as a required status check on the branch, so a branch protection rule, you can't merge that branch until the test passes.
Okay,
You could probably have the action close the pull request, but then you would give the action permission to do something on the repo.
What about where you asked earlier about how to test the GitHub action? So how do you usually test the GitHub action?
So I test the dumper. So I just make I make a new repo. So I make another repo on GitHub, not fork, just a new repo, and I push up my stuff, and then I commit the action like crazy and test it. If someone has better ideas, I feel like there's a VS Code extension that like really nicely check actions. But yeah, I push and trigger them. And I tend to, when I start, I always put a manual dispatch so I can click it and trigger. But yeah, that's it. There's better ways to do it. I don't.
We use issue and pull request templates, and
Yeah.
and I find that to be really useful, because then if you it's thrown up a little barrier. Like if you're going to open an issue, we want to know all this information about the issue that you want us to work on. So.
Yeah, I definitely second that. We do it with bug reports. Again, technical solutions solve the problem. Like people who won't give you enough information.
Yes.
And if you give them like this nice, it is a barrier, but it's super helpful. And I think it's the same with the book. Like you have you actually update the documentation and take those blocks. And I think like a bot telling you something's wrong, people are like more accepting of than if it's like me. Is it different? No, but I think people respond a bit better to like something to fill in, like an alternate thing.
Jim has a suggestion on how to, do this thing.
Yeah, that's because one of our students, Anderson, who works at Sandia now, he did all sorts of action testing, and I think he squished 2,000 commits into one. Thanks, Jim. I can't read that from my far away. Oh, nice, yeah, love functions. All right.
Any last comments or questions? Yeah, well, if you think of something later, I think Helen loves to talk about Git, so. Thank you very much, Helen. Okay, so our next speaker is Juniper Tyree. They're from the University of Helsinki and will be talking to us about compression safeguards. And just get Juniper on the screen.
Hello, can you hear me?
Yes. Yes, I can. Yeah, go ahead.
Can you see my little laser pointer?
Yeah, oh, the slides just went away.
The slides just went away.
Please try sharing it.
Yes. Let's restart that. And share.
Oh, there they are.
And you can see it.
Yeah.
And you can see the laser pointer.
Yeah.
And when I change the slide, you also see it.
Yeah.
Perfect. Okay. then let's get started. So hello, good morning, everyone. I'm Juniper Tyree. I'm a PhD student at the University of Helsinki in Finland. This is actually the university where Linus Torvalds studied and developed Linux at. And today I'm going to talk about lossy compression, and in particular my work on what I'm calling compression safeguards to make lossy compression safe and fearless. Now, those are quite some big words, quite some emotive words. So I want to first explain why there currently is fear about lossy compression, and then present the solution that I and my collaborators have been working on. But first, maybe let's get started by talking about why we actually need to talk about lossy compression. And so I'm working in the weather and climate modeling space, and there we have seen the enormous growth in the amount of data that we're producing. In Europe, we have ECMWF, the European Center for Mid-Range Weather Forecasts, and that has a huge archive of all of our weather and climate forecasts. And here you can see a graph of how that has grown in size. This might not look very bad. Unfortunately, as time has gone on, we actually have a plot with a logarithmic axis, so we have exponential growth. And it's not slowing down anytime soon. And of course, data storage, data transfer, data operations all take time, all cost something. We never want to get to the point where sort of our storage fills up, and we have to limit the science we can do. So we need to have a way to figure out how to store more data in the same amount of space or less space. And this is where data compression comes in. And typically, people have been using lossless compression, but for scientific floating point data, the compression ratios you can get with that, sort of 2 to 6, sometimes above, just are not good enough anymore. So what we need instead is a different class of compression methods called lossy compression methods. The lossy here refers to the fact that we will now actually be losing something, some information, some detail, some resolution, some features, something will be lost. But on the other hand, for this loss, we're getting something, namely higher compression ratios. So that goes from factor 10, factor 100, some methods even promise a factor of 1,000. So that sounds very nice, problem solved, right? Unfortunately not, because this lossy part is actually quite scary. We don't want to lose important information in our data. So lossy compression is scary, and rightfully so. The sort of first response to that from the compression community was error-bounded compression. So where we can bound, for instance, the absolute error in between the original data and the decompressed data. But that's unfortunately not enough to actually preserve all of the important features that we care about. And if we want to be able to use lossy compression, then really it needs to be safe. So we can't have anything go wrong, because if we want to then work with any lossy compressed data, we want to make sure that, for instance, all the analysis we run on that come up with statistically the same results. So we really need some safe compression. Now, to motivate with some examples of it, why lossy compression actually is that scary, I'm going to present sort of 3 groups of things that can go wrong. And the first one is bugs, undefined behavior, sort of anything normal where compression is just software has bugs, something unexpected might happen. In this example on the left, we have some satellite data with a lot of missing data, which you can see with those pink crosses. And I've compressed that and decompressed that with the ACID-free compressor version 3.2. And you can see suddenly the missing data is gone. It has just hallucinated some data in there. This bug was reported and fixed by me, but before then nobody had noticed. And so that can, of course, just slip in, and you wouldn't want to compress your data, your important data, and have something like that happen to it. That would be very scary and unsafe. And other compressors often have similar issues around missing data or their special values. Another thing that can happen is data invariants that are violated. For this example, we have some precipitation observations, just a simple time line for 2 observation stations. On the left, the original one-dimensional observation. On the right, the compressed version, here with ZFP. At first, this looks really nice, nicely preserved, so all good. Unfortunately not. If we look into a core property of precipitation, namely that it's 0 positive, and put that on a timeline, and let's zoom in a bit on that. We have in the original data sort of time periods when there was precipitation and time periods where there was not. And now in the compressed data, 3 things can go wrong. We have some false negatives. So suddenly precipitation is gone. It's 0 where it shouldn't be. We have false positives. It has invented some precipitation. But even worse, we have some negative precipitation. So now some physical invariants are being violated. And we really don't want that. And a final class of things that can go wrong is application requirements. So on the left here, we have some wind data, the UV vectors, and I might want to later compute the vorticity on that. For that, I need to compute the spatial derivatives over both the U and V axis, well, the latitude and longitude axes. And if we do that, we would probably want to then preserve an actual error on this derived quantity, so this derived vorticity, not just on the original data. We can do a lot of guessing here. We can even be a bit clever in guessing, but most of the time, people will just put something in and then, well, you might get an error bound violation on some application-specific function you would later want to compute. And so here again, if we don't really know about these requirements, if we don't care about them enough, then violations of requirements we do have might happen, and that can make lossy compression quite scary. So to summarize, lossy compression really is scary. So let's move towards the solution that I've been working on. And of course, it's not the only solution, but sort of extends the space of solution that now exists for this problem. So I want to make lossy compression safe and fearless. So the safe part is clear that if you have safety requirements, they should be met. And then it becomes fearless because we no longer have to be scared about lossy compression destroying some important information that we have. And for me, the really important point here is to make this end user focused. So really for the person who's going to be working with the data, analyzing their data, who has their data specific and application specific requirements that need to be preserved. And what I've been working on, I'm calling compression safeguards. Now, what are those compression safeguards? They consist of sort of 2.5 parts. The first one is the most important one, is to really declare your safety requirements as a user. So what are the properties, the features of the data you really care about and you want to have preserved? That might be something as trivial as missing data should remain missing data. It might be something simple and already well supported, like an error bound should be kept. It might be something more complex, like a derivative must be error bounded, or something even higher order than that. The next step is the safeguards provide an absolute guarantee, no matter what, that those requirements are met. And this sort of goes a bit in connection with the third part, that you can use the safeguards with any existing compressor. So the safeguards are not a new compressor, it's more another tool in your toolbox where, independent of what compressor you're currently using, if you tell the safeguards what user requirements, what safety requirements you have, they can guarantee that no matter what, you will be safe and those requirements will be met. i.e. if the compressor you're using does violate them, the safeguards jump in, recognize that, and then correct it. And we have in our implementation, in our reference implementation, some existing bindings to make that easy to use. For instance, with the Python compression API num codex, or if you have large chunk data with XArray, where then problems like having safety conditions that cross chunk boundaries are resolved and dealt with. So to summarize a bit, the idea behind safeguards is they guarantee you safety, given your user requirements, your safety requirements for any given compressor. And for me, the sort of important point, apart from we have this absolute guarantee, is really it's about you, the end user, and what you need from the safeguards. So I wanted to give a bit more insight in sort of what kinds of safety requirements we can guarantee already and what things we might be we're working towards in the future. So let's start a bit simple and then move to more complex and also more novel things in the solution space of providing safety. So on the very basic step is just sort of basic data properties. Keep missing values missing, keep global extrema, keep the sign of the data the same, keep some special values, etc. Not all of those are supported by other compressors or other other solutions in the space, but sort of those are very simple to provide. The next step up, also quite well supported, is just error bounds of the data. Those are usually pointwise, so we support absolute relative ratio error bounds. not very much new here. But now it's sort of gonna get a bit more interesting when we move to error bounds on derived quantities of interest. So we're now looking at error bounds on a function over the data, f of x. And again, we'll start simple. So just any pointwise function you can think of, for instance, the square of the data. But we can do better. We can do functions over local neighborhoods. So for instance, any derivative that you might approximate with a finite difference. And one key important feature we have here is boundary conditions. So if your data wraps around, we can deal with that. We can make sure that also like you don't have any violations near the boundaries. Same thing for if your data is chunked, we make sure there are no violations near the chunk boundaries. We don't just support linear functions, but also anything nonlinear. So here just x divided by the sine of x is supported. We support any piecewise function, not just sort of one, but also, well, nested piecewise functions. So this is one activation function in machine learning that I just copied over here, where we say if the original data is bigger than 0, we want to preserve an error in the original data, otherwise an exponential function based on it. Then next up, we also have support for auxiliary constants that can appear in our derived function. And those can be sort of constant at just a single scalar value, but they can also vary over the entire data range. And this makes it very powerful because then you can really just plug any other data in there. Something you might commonly do is, for instance, plug in the coordinate axis. So for instance, the latitude or longitude into your function. And then it can just be included in the quantity of interest in the safeguards. We'll be able to derive your safety requirements from that. The next big feature is regionally varying safeguards. This is commonly known as regions of interest. Typically, this is implemented by just sort of declaring 2 regions, A and B, and then you have sort of one requirement in region A and one requirement in region B. But we offer a bit more flexibility here. Mainly that a lot of the parameters in the safeguards, for instance, the error bounds can be pointwise. So they can vary differently for each data point. And then, of course, that makes it very trivial to vary them in different regions of the data. And those regions don't have to be discrete. They can be very smooth and anything you can come up with. And finally, sort of a bit of the killing features, you can do arbitrary logical combinations of all of those above. So you can have an any combination, that's sort of a logical OR. So for every data point, you want to preserve safeguard A or safeguard B or safeguard C. And of course, this gets really interesting if those safeguards are not pointwise. For instance, if you're preserving a derivative, then it's not just as simple as just considering the requirements for a single data point because they can affect neighborhoods. The next one, logical AND, is a bit simpler. And then finally, we also support a selection. So where you have an arbitrary number of other safeguards and then a mask that says sort of for each data point, which of those do you actually want to preserve? And this is also a way where you can then implement or provide very discrete regions of interest. So to summarize, we're very flexible. We guarantee always that any arbitrary safety requirement you throw at us, they're met. And really the points where we provide specific novelty here is in this flexibility, arbitrary combinations, and making sure that it's not just pointwise safety conditions, but also conditions over local neighborhoods, over stencils with boundary condition. Sort of anything you could describe in prose, we try to also be able to support that. To quickly showcase what this looks like, let's go back for our examples. So in the example of missing data, I'm now going to sort of overlay what the safeguards look like once they've been applied. And I mean, it's going to be boring. It usually looks as before. And at the bottom, we have sort of how they are configured. In this case, we just have a safeguard that, in this case, just says, yeah, we want to have an absolute error bound. And please make sure NANDs are dealt with properly. For the precipitation case, here it's actually enough to just preserve the sign of the data. So we add an additional safeguard saying, please preserve the sign. And then for the vorticity case, it gets a bit more complex because now we want to actually express the entire formula that computes this. So I've omitted the exact details, but they're in an appendix later if you want to see them. But again, it's just an error bound now over a quantity of interest and a neighborhood, since we're computing derivatives. As a very brief overview of how safeguards actually work, they're sort of relatively similar at the very high level to other correction methods that already exist, where we take the original data, we take the decompressed data, then we first check if any safety requirements are violated. And if they are, we compute a correction. What makes the safeguard sort of different here is that our correction is not just, well, we'll just losslessly compress any violations we have. No, we actually analyze the safety requirements you have and then derive something that compresses better than just lossless compressions. And this can be applied not just to compression, but also other methods like AI. And yeah, whereas before a safety check might fail, in the end it succeeds. An important point to make is sort of the worst and best case, what happens with the safeguards. In the worst case, you have a really bad compressor. So you're still safe, but you might lose a lot of compression ratio since the safeguards need to do a lot of work. In the best case, of course, you have a safe compressor. So the safeguards just make sure you're safe and do nothing else. So they still give you sort of that trust, but don't actually change your compression ratio at all. And then there's sort of the synergy space in the middle where the safeguards can also be used to correct sort of a few outliers, but a bit more cleverly than existing methods. And sort of to summarize that, you always get safety, but we try to produce well-compressible corrections that guarantee this. To very briefly, since time is running low, also talk a bit about the limitations. The first one is quite fundamental. You are trading off compute and compression ratios for safety, but I think that's a very worthy trade-off to make. So since we want that safety, we will need, if the underlying compressor doesn't provide it, some corrections. Those corrections are pointwise, and that might bottleneck your compression ratio if your underlying compressor really is bad. But it's still better than being unsafe and not knowing it. The next one is a bit sort of in our implementation where right now we're producing one-shot corrections, so without any iterations. That makes them very composable and reasonably fast, but they're not always optimal. So we're still working on ways to sort of optimize this. And then finally, of course, there's always more to support, more safeguards. In particular, we want to support more global safeguards like a mean error, like preserving the bias or reducing the bias of your compressed data, supporting unstructured grids, supporting incremental corrections. There was always a little more work to do, of course, and we're hoping to continue working on that. So to summarize, compression safeguards are not meant there to replace any of your compressors, but they're meant to keep you safe, no matter which compressor you use and no matter which safety requirements you have. And with that, thank you very much for your attention. And if you want to learn more, I am convening a session and short course at EDU next year, where they will also be showcased and demonstrated, and you can try them out yourself.
Great, thank you very much, Juniper. That was really interesting. Do we have any questions? A lot of questions. Okay, Mike.
So I'll preface this by saying, like, I know very little about compression, so this question might not make any sense. But like in your example of preserving the mask, like you talk about how the safeguard will reduce your compression ratio, but it seems like you could also preserve the compression ratio and just do a worse job. Like you could have a bigger error in the data that is not masked out in the compression. Like how do you balance it? Like, have you looked at that kind of error metric of like, I preserve the compression ratio, but apply the mask, or preserve zeros and or preserve the sign? Like how much worse does the data look when you keep these safeguards in place?
I'm not fully sure if I got everything, so I'll try to respond to how I've understood it. To my understanding, you were asking about sort of, why can't we just have higher error bounds, or maybe not regard all of those safety requirements?
I think like you talk about keeping the same error bounds and you lose in your compression factor. But if you lower your or increase your error bounds, if you allow bigger errors and try to keep the same compression factor, like how much bigger do those error bounds get?
I'm still struggling a bit. So I think, well, there are two things you can do. Of course, you can always, if you just keep your original compressor, you can like lower the error bound, make it tighter until it sort of by itself is safe to use. The unfortunate case is that oftentimes that might require you lowering the error bound to 0. So then you tank your compression ratio, but you make it safe. The other way around, if your compressor doesn't by itself preserve your features, invariants, etc., then you need to do some extra effort to correct that. And the approach the safeguards take is sort of they treat the compressors as a black box, so they only can add something on at the end. And the only thing they can do is make sure that whatever they add makes your safety requirements pass, and that whatever they add compresses well. Of course, if your compressor itself implements all of this, they can usually be a bit more clever and can maybe even preserve compression ratio. And so in an ideal world, would all of the scientific compressors sort of start implementing loads of different error bounds, quantities of interest, and sort of, for instance, preserving the range of the data, etc.? Absolutely. But that places a huge requirement on lots of different groups to implement that. And then we would still need to trust them that they don't introduce bugs, etc. So the approach of the safeguards is a bit different. They're more user-focused, where you as the end user, well, you don't want your safety requirements to be violated. So no matter what the compressors does, you stay safe. If the compressors improve and actually get safe by themselves, then the safeguards still keep you protected, but sort of have to do less work. In terms of how much your compression ratios change with the safeguards, it depends a lot on the problem. At the moment, if you have a sort of pointwise safety condition, so for instance, just bounding the error on the data itself or on a pointwise quantity of interest, you only pay the cost for sort of as many violations as there are. If you have those safety requirements over neighborhoods, then of course, because now safety conditions sort of are a bit more effective, then your compression ratio goes down more. And then the last sort of variable there is how adversarial the compressor is. So if your compressor is very well behaved, gets relatively predictable outputs, then the corrections will also be predictable and therefore easier to compress. But if you build a compressor that sort of just spits out random data, then the corrections, the safeguards in the computer are just as random. And then of course that doesn't compress well at all. I'm hoping I sort of answered at least some of your questions. But if you still have some, maybe you can write in the chat and I can answer later when I sort of can think about your wording a bit longer.
Thank you. Maybe one more quick question. Did you have a?
Yeah, well, this is a fantastic piece of work. I really think that this area needs a tool like this. In your experience with different compressors, did you find that they are following same definitions and implementation standards? Because there have been works which examined the previous compressors' error boundedness claims, and there were some gaps. So what's your experience in this area?
Already sort of the definitions can be quite different. My favorite example there is relative error bounds, where whether a compressor means by that a sort of range relative error bounds, so essentially a percentage based on just the maximum minus minimum of the data, or if it's actually a sort of relative towards the individual value. It changes by a compressor, and whether they document that well, it doesn't happen often. So that's already where, as the end user, what relative means can be a bit obscure. And then, yeah, in terms of sort of what errors they provide, if they actually do guarantee them, there's a lot of variance. As I showed with the bugs, there was a paper, I think, published 1 or 2 years ago that showed that SF3 does preserve missing data, and then sort of I tested a year later and it no longer does. So those things can happen over time. And then, of course, every compressor also has its sort of own strategy for how to preserve errors. A lot of the sort of newer ones are now adapting this general idea of first you compress and then you correct. But
Oh, yeah.
most of those that do the corrections just do a lossless correction. And so even though there's now sort of an emerging approach there, that's a bit similar in idea to the safeguards, even though the safeguards have a sort of more, well, we don't just losslessly compress our corrections approach. There is sort of some more general idea emerging there in the field.
Thanks, Phil.
All right, thank you. I think we'll stop here. Thanks a lot, Juniper, for a great talk.
Thank you.
And now we have a 25-minute break until 10:40, so see you back then.
Welcome back, everybody. We're gonna get started. We have 4 talks coming up now. I'll tell the speakers, we'll try to aim for about 17 to 18 minutes for the talk and 2 to 3 minutes for questions. First up, I'd like to introduce Tripti Agarwal. She's finishing up her PhD in Ganesh's group at the University of Utah, and she's gonna be talking about some of the work she's doing on lossy compression as well. For a fun fact about Tripti, she's also a big snowboarder and likes to go to Big Sky and anywhere around Utah too. So yeah. So take it away. Thank you.
Thank you, Brian, for my introduction. Okay. Yeah, perfect. Okay, hi everyone. I'm Tripti. I'm a PhD student at University of Utah, and I work with Professor Ganesh Gopalakrishnan, who is also at University of Utah. And today I'll be talking about my work and some of the initial ideas that we have on formal guarantees of error-bounded lossy compression. This work is going to explore how we can formally verify correctness and determinism in lossy compressors while maintaining topological and numerical integrity. So let's have a quick understanding of why we are working on lossy compressors first. So scientific discovery today heavily depends on large-scale simulation and high-resolution instruments. For instance, a single CSM climate simulation can generate 1 terabyte of data per compute day, and that can consume nearly half of the NCAR's hardware budget. Similarly, cosmology simulation produces a total of more than 20 petabytes of data, and X-ray experiments can reach terabytes per second. So clearly, the scale of data in modern scientific simulation is staggering. From climate and cosmology to X-ray facilities, we are generating large amount of data. And storing, moving, and analyzing this data becomes infeasible unless we reduce it efficiently. So this brings us to the next key question: how can we actually reduce this data without losing important information? Well, the first approach that we typically use is a lossless compression. Lossless compression basically relies on redundancy, that is, repeated patterns or correlation in the data, to shrink the storage footprint without changing any values. So, for example, here's a simple workflow of how a lossless compression looks like. What we do is we basically take the input data, then pre-process it using some of the techniques that are already available, like LZ77, Snappy, or zlib, so that we can remove the redundancy that we are talking about in the data and then apply entropy encoding, such as Huffman encoding, on the data. And then we basically store the compressed output in forms of smaller bytes. But for scientific floating point data, where we have huge amount of data, the compression ratio that we can achieve is 2 to 6, or I mean, mostly it's around the factor of 2. So to increase this compression ratio by more than 2, we must trade a bit of accuracy for a much higher compression ratio. That's where the lossy compression comes in. So a lossy compression basically reduces the precision through quantization. What happens in quantization is that the floating point values are basically converted to like a lower precision or integer bins, which are later converted back during decompression into floating point values. But during this process, we get a lower precision output. Well, in this process, we deliberately do this to sacrifice some of the numerical precision to achieve much higher compression ratio. Using lossy compression, the compression ratios can go from 10s to 50s to even 100s, or sometimes thousands more in lossy compression. But the key here is the balance. We want to make the data smaller, but still accurate enough for scientific analysis. And to understand this balance, how this balance is basically measured, we look at the metrics so that we can quantify the impact of the lossy compression that we are applying. The impact that is we can measure it quantitatively using metrics like error bounds, PSNR, SSIMs, or visually through topological descriptors such as critical points, merge trees, or contour trees. So here is an example of hurricane data using different lossy compressors. Particularly, we use CFP and SE, and their quantitative metrics here. So SE and CFP are the two main lossy compressors for floating point data. At least that's what I use mostly. And these are built by the Argonne National Lab and Lawrence Livermore National Lab, respectively. The quantitative assessment in the lossy compressors is basically done by defining the point-wise error bound and calculating the statistical metric like root mean square error, PSNR, and rate distortions. In this example, we can see that different compressors produce different values of PSNR and SSIM. These values helps in measuring the reconstruction quality of the data. And these values are highly dependent on the point-wise error bound that we define while performing the compression. So the next question is, how do we define a point-wise error bound? Well, the point-wise error bound is defined in two ways. One is using the absolute error bound, and the other is a relative error bound. The main idea of defining the point-wise error bound is to know how far the recompressed data can deviate from the original data. Okay, so we have this literature of how the lossy compression works, but let's just switch gears and talk about some of the problems that we face in lossy compression. And as discussed in the previous presentation as well, what are the features of lossy compression, but from a slightly different angle. So far we have looked at the compressors like SE and CFP and defined point-wise error bounds like absolute and relative, ensuring that the reconstructed value don't deviate from the original by more than the user-defined error bound. But the big question is, do these guarantees always hold? Well, in practice, the answer is no. Even a tiny rounding effect in floating point arithmetic can sometimes push values across those mathematical boundaries that we have defined. And in reality, floating point numbers can't represent every possible real value. For example, this is when we quantize or round the data, especially near the bin edges. We can unintentionally violate the very error bound we are trying to enforce. And that's where many subtle correctness issues begin. We also face undefined behaviors like nans and infinities. If the original data contains nans and infinities, these values can propagate through different stages of lossy compression pipeline and result in much higher error in the reconstructed value. Similarly, the normals are highly sensitive to rounding, and these can propagate unpredictably through the pipeline. So in this work, one of our goals is to eliminate these corner case violations, that is these error bound violation or undefined floating point behavior during the compression and the reconstruction pipeline. And for this, we propose and define formal contracts, such as the pre and post conditions, ensuring that the difference between the original and the reconstructed data is less than or equal to the defined error bound, and that the quantization does remain monotonic, bounded, and terminating. We encode these contracts using Verus, which is a Rust-based verification language that reasons about the memory safety and arithmetic correctness. This gives us specification level guarantees that the reconstructed values never violate the user-defined error bounds. So the next problem that can happen in lossy compression is the race condition. Since most of the modern compressors rely on OpenMP or CUDA parallelism, and this parallelism is important because we want to produce scientific analysis faster. But the uncontrolled shared spaces can lead to data race, producing non-deterministic results, even if we have the same inputs. And this can definitely break down the correctness guarantees of our system. Well, if we use Verus, it can help eliminate this by enforcing the ownership and the borrowing model where we have each thread can operate on a disjoint memory, and by permission-based reasoning, which can statistically prevent two threads from writing to the same cell. So basically, if we use various kernels, that can help remove race condition as well by construction itself. One of the next interesting problem that we want to tackle in lossy compression is in terms of visualization. The scientists really rely on how we can visualize the data, and we are interested in not having any problems during the visualization. So basically what we have beyond the numerical accuracy is topology that can help tell us the structure of the data and whether it's preserved or not. And there are different types of topological descriptors that exist. For example, the first is like critical points. Critical points such as like maxima, minima, and saddles capture the physical features such as vortex cores or pressure extremas. These are the points where the derivative of the function is 0 or undefined. These helps it to quantify and describe the structure of the system. For example, the white dots here are basically representing the critical points on this data. Similar to critical points, we have contour trees. Well, contour trees records the connectivity between the isosurfaces or the contours on a scalar field as their ISO values keeps changing. For example, in this graph, we can where f is a height function, we can create a contour tree by connecting the critical points. That is, the blues are the minimas, then the whites are saddles, and the red ones are the maximas at different isosurfaces to obtain the contour tree that you see on the very right. No, left. Sorry. Other descriptors also exist like merge trees, Musk-Mill complexes, and these helps to summarize how the scalar field will evolve. So basically here is an example of how a merge tree looks and how does a Musk-Mill complex look for any 2D scalar function. However, there is a problem that can occur in topological descriptors because of the loss of information that we have during the quantization process. Basically, the lossy compressors can introduce false positives, false negatives, and false types in these structures. What is a false positive? A false positive basically refers to when a new feature is being introduced to your descriptor when it was not actually available in your original data. Similarly, a false negative is the loss of feature in the reconstructed data, and a false type is a new type of feature that can get introduced in the reconstructed data when it was not really in the actual original topological descriptor that we designed for the original data. And this is a well-known problem in the community, and many methods try to attempt and solve this issue, where they try to remove these false cases by saving some extra information while compressing, and then applying the specialized techniques to retrieve the information correctly. But most of these methods are iterative and computationally expensive. Prior work such as TopoSE and TopoQZ tackle this issue. But these methods are bottlenecked by the topological descriptor creation during the compression pipeline, thereby making the entire process computationally expensive and memory expensive as well. And since one of the main advantage of lossy compressor is speed, and we do end up losing this speed during in some of these prior work, we are interested in building a compression pipeline that is much more faster, but can still preserve these topological information. Hence, we address this issue with a faster single pass approach. Our single pass method directly preserves critical point types, locations, and thereby also preserves the merge tree structure during compression. This work is under progress and is in collaboration with Argonne National Lab. So for this, we use stencil-based neighborhood analysis to detect these features and store the minimal metadata to reconstruct the topology as accurately as possible. So here's an example of a maxima point in the original data that do get lost during the quantization process. And when we decompress it, we actually is not able to retrieve the maxima back. So what we can do is basically have a maxima stencil applied on the decompressed data, because we do know that that point needs to be a maxima for its surrounding neighbors. And the mechanism for maxima stencil is very simple. We just take the maximum value of the neighborhood point and add a machine epsilon to retrieve the final maxima back. This basically avoids the iterative reconstruction that we were doing in some of the prior works. We also have to save the relative positions of the critical points so that we can retrieve the merge tree. Because merge tree structure, these merge trees are basically can identify what is the structure of your data, what was the structure in the original data, and is it really saved during your decompression process or not. So for example, let's say these are two different blocks of the original data, and these are the two maximas of these blocks. When you apply the normal stencil that I was talking in the previous slide, we might end up getting two maximas, but of the same values. But you do see that there is a relation between these two maximas, that this block 1 has a lower maxima than the maxima that you obtain in the block 2. And we want to preserve this relative positioning as well. So rather what we can do is just save the relative position of each of these values during the quantization process. And then when you want to retrieve the correct output, you can just decompress it by multiplying it by the relative position that you have. And this position basically helps in preserving the overall merge tree structure as well. And believe me, it does. We have tested it, it's just not added it here. So to wrap up, let's revisit why formal guarantees matter in lossy compression. So in practice, we have 4 major sources of uncertainty. 1, the error bound that can violate due to the rounding effect. Second, the floating point behavior that leads to non-deterministic results. Third is a race condition in the parallel implementation. And fourth is the topological distortion that can alter the scientific meaning of the data. Each of these can independently break correctness, and together they can make the reliable lossy compression extremely challenging. And our first line of defense is formal verification using Veris, a Rust-based verification framework. By expressing these pre- and post-conditions in the compression kernel, we can mathematically prove that the error bounds always hold for all valid inputs. This ensures that the decompression is both correct and deterministic, and not just empirically accurate. With Veris, we also eliminate the race condition issue through its ownership and with the permission-based reasoning model that is available in Veris. Finally, we also address the structural integrity of the scientific data. Our single-pass topology preservation method captures the critical points as the maxima, minima, and saddles directly during compression, along with their connectivity in the merge tree. Together, these components will form a comprehensive, correct framework for lossy compressors, such as like SE and CFP. Thank you.
Any questions for Tripti? Yes. I don't know anything about Veris, but so I was, just to clarify, is this like a tool that you're implementing your compression algorithm on top of, or is it like a separate analysis tool?
So this is going to be a separate analysis tool.
Okay.
Yeah.
I was trying to figure out, we've like talked about other formal proof tools that we have here. Is this something that works on your code, or do you have to reformulate your algorithm in a way that Veris can read it?
So the algorithm will remain same, but it's going to be separate from the actual tool that exists in the HPC or the scientific compressor, lossy compressor world. But it's a separate algorithm that we have to implement. But the logic will remain the same with the correctness guarantees and the safeguards that we want to apply here.
Okay.
Yeah.
Makes sense.
But the topology part is something that we are implementing in the compressor itself. So because that's more of how the data can be processed and how we can save some of the metadata. So the topology part is like, you can say, you can call it like, we can add it as a flag, and it can run with, so right now I'm working with the SC compressor, and we are adding it into the SC compressor itself. Hopefully one day we'll have all the correctness guarantees as well in the compressor directly. Yeah. Thank you.
We do have another question online, but I'm gonna, and we also, clearly, it's the great thing of this workshop, we have a connection to talk about shared research already. But Juniper, given the time constraints, I'm gonna let you guys tackle that offline and move us on to the next talk. So, thank you. Okay, Niclas, you're there. Okay, so Niclas is a research software engineer at the German Climate Computing Center. And he'll be talking about his work on the high performance climate weather benchmark suite. He also does some other work on specialized hardware that brings together storage and compute to minimize data movement, which would be a really neat talk to hear too at a performance workshop. So hopefully we'll have one of those at some point. So Niclas, go ahead.
Sure thing. Thank you very much. 1 second. Let me just grab the screen share real quick. All right. I think you should be able to see these slides now. And you should also be, yes, I can see that the slides are changing as well. Very good. Okay. So yeah, thank you very much for the introduction. I'm here today to talk about HPCW, which is short for High Performance Climate and Weather Benchmark. It's actually a benchmark suite. That's what we'll get into right from the start. So I'm going to talk about HPCW in general, first and foremost. If you attended the first version of this workshop from 2 years ago, I think, you might remember HPCW. But a lot has changed since then. So even if you attended that, you'll probably still get some useful information out of this. After the introduction, I'll talk a little bit more about the topic of this workshop. So we're going to talk about reproducibility through the lens of, benchmark creation. And if there's some time left, I'll provide some usage examples as well. So let's begin with the introduction. What exactly is HPCW? As mentioned, it's a benchmark suite, which beckons the question, really, do we need another one? Like, at this point, there are so many different benchmarks in the HPC world. And that's a fair point, right? We've had benchmarks for as long as the field exists. We have things like HPL, we've got Stream, and they're all good benchmarks. They all have their purpose, but they don't really capture what we are doing in climate and weather science. They're not really capturing the computational, the communication patterns, all of these things. And even benchmarks like HPCG, which are, a valiant effort at being closer to actual applications, they don't really capture our domain. So what we ended up doing is we figured that it would be high time to actually provide such a benchmark suite for our community. And that's why HPCW exists nowadays. Another question that usually arises in these cases is, why do we need a benchmark suite actually? Like, what can you do with it? And there are many, many different answers to this question. My favorite one, though, is co-design. Co-design, talking not just about hardware, but also about the software side of things, called science here on this side, because it's really not just about the software that we are using in the sense of, compilers, libraries, and everything, but it's also about the numerical methods that we are using to solve all of our problems. And having a benchmark suite would be really nice, because in this case, we have a meaningful application that we can actually use to show what it is that we're trying to do, right? So if we're communicating with hardware vendors, for example, we can actually give them something and say, hey, this is what we're trying to do with your hardware. Please provide us with a system that actually works well for these use cases. And ideally, we would end up with a system that is specifically tailored towards our domain. And yeah, HPCW aims to be that kind of meaningful application. At a very high level, if we want to talk about HPCW here, as I said, it's a benchmark suite. So this already implies that we have multiple applications in here. We'll start with the smallest ones right here. We're talking about EC Trans, EC RAD, and Cloud SC. Those are dwarfs or mini applications that were actually extracted from the IFS. Each of them is responsible for a different part of the code there. EC-trans, for example, is responsible for the spectral transfers, all of them really. So this is basically the most costly component of the entire code. EC-RAD does the radiation stuff. CloudSC is for the cloud microphysics, and yeah, they all together are quite representative of what IFS actually does without requiring you to build IFS itself. We are further complementing this with another mini app. In this case, it's the DAI core of the Japanese NICA model. And alongside these mini applications, we also have full-blown models in our benchmark suite, namely Icon and Nemo. For each application, we have multiple test cases. We've got validation in place as well. And the core idea, or the core ideals really, that we are trying to follow here is we're trying to provide relevant and realistic test cases that are actually found in our domain. Maybe even operational setups, near operational setups, which is actually used on, on today's hardware as well, which is mainly pre-exascale still. So I already mentioned that a lot has changed in the last few years regarding HPCW. The most notable change is probably the open source release. So a few months ago at this point, I think 4 months ago, 3 months, something like that, we released HPCW with an open source model, which means after the talk, if you're curious, you can just go ahead and play with HPCW yourself. If you attended the first version of this workshop and have exceptionally good memory, you might remember that the application list looked a little bit different the last time around. One of the moves that we also had to make for this release was we had to consolidate down a little bit. So remove all of the non-open source stuff, remove components that are not relevant anymore. And this consolidation really helped us with getting an actual package that we can maintain and really stand behind. Something else that has changed in the last few years is that we've demonstrated the feasibility of this project, of this benchmark suite across many different systems at this point. So this doesn't just run on the DKRZ system or Eviden in-house systems anymore. We've also ported it to Fugaku, to Mare Nostrum 5. We're currently porting it to Lumi, and sometime soon we'll also do the port to Jupiter as well. A very brief technical description. All of this is basically driven by CMake. So the build process is all CMake. Ideally, if you want to port HPCW to your system, all you have to provide are 3 files to describe your system environment. So basically talking about the compiler and how many resources you want to apply to a certain test case. This low number of configuration options allowed us to, for example, do the Mare Nostrum port in less than 2 days. So once again, if you're interested, you can look at the repository afterwards. And I could probably go on and on about the technical side of this project, or the challenges that we faced during the ports, which then themselves fed back into the improvement of HPCW. But I think it would be a better idea at a reproducibility and correctness workshop to also talk about reproducibility. So let's actually talk about reproducibility, but once again through the lens of a benchmark creator. But before we do that, let's actually take a step back and decompose benchmarks in general. So try to break it down into the essential components, really. And usually you have 4 components for any given benchmark. You have some form of code that you want to benchmark. You have certain test cases, which are defined on this code. You have some form of validation to ensure that your test cases actually computed what you intended them to, and you didn't just convert electricity to heat. And you have some sort of metrics so that you can actually compare your runs afterwards, be it between different machines, on the same machine, doesn't really matter. Just having some form of number that you can, or multiple numbers, that you can compare afterwards. So let's look at each of these components individually and how we address these things in HPCW with reproducibility in mind. Beginning with the code to benchmark, and of course, I already mentioned it, we have multiple applications in here, and the bare minimum that you have to do really is pin the versions of your benchmark applications. That's a no-brainer, really, right? You want to compare apples to apples. It's not really a good comparison to, for example, run a certain test case with an icon version from 3 years ago and compare that to the release from last week. That's not really fair. So keeping that in mind, that's the bare minimum, but you can very easily go a step further, right? Especially if we, once again, talk about icon, for example, there are a lot of dependencies. BLAS libraries, for example. And as we all know, swapping out BLAS libraries or sometimes even changing versions of the same BLAS library can lead to slight differences in your results. So what we did in HPCW, in the interest of improving reproducibility across different architectures, different systems, is we tried to pin the versions of the dependencies. But this is also where you have to make a sort of trade-off, which is why we actually made the usage of these pin versions of the dependencies optional. The trade-off that I'm talking about here is reproducibility versus mainly performance and also feasibility to some extent. Sticking with the example of BLAS libraries, many different high-performance systems have specifically tailored BLAS libraries. Fugaku is a great example. There, the BLAS library is basically integrated into the compiler. And if you run anything on that system, you would be, or you would do a lot better if you actually used that particular BLAS library instead of OpenBLAS or MKL or anything else, really. So that's really why we made the usage of these pinned dependencies optional to not drop the ball on the performance side of things. After all, it's called high-performance computing, right? It's in the name. Also, we're not providing dependencies like the compiler or MPI libraries either. That's just not feasible, really. Those are also usually tailored towards systems. So at some point, you have to make these trade-offs anyways, just out of a feasibility issue, really. Okay, that was a lot regarding this first point. But once you've pinned the applications properly, getting reproducible test cases is rather simple. Whoops, let me just move that. All you have to do is provide all of the arguments, all of the input files, make sure that there's no random number generation left anywhere, and all of a sudden you have reproducible test cases. HPCW also provides all of these input files that we need for the bigger test cases as well, so you don't have to think about these things either. So at that point, we can basically just skip and talk about validation. Now, this is where it gets a little bit more interesting again. How do you actually verify all of these different test cases on the different applications? And to get the obvious part out of the way, bitwise reproducibility is not an option. We're talking about comparing different applications across different system architectures at this point, right? It's not just x86 anymore. We've got ARM systems, we've got GPUs, we've got almost operational RISC-V systems at this point. And trying to basically enforce bitwise reproducibility is, from a benchmarking standpoint of view, not an option at all. For most other use cases, it's also not an option anymore, but that's besides the point. So what do we do instead? Well, it's basically some form of numerical validation that we have to specialize per application, sometimes even per test case. Numerical validation in this case really just refers to checking against some reference values and tolerances and making sure that certain parts of your output are within this predefined interval. The generation of these reference values and tolerances is, once again, very interesting though, because with the different test cases, you have very different scenarios. So sticking with the icon example, once again, we've got multiple test cases there. One of them is a Hadley test, which basically has a known solution. Validating these types of test cases is, of course, rather simple. You just check how far you are away from your known solution. And if that is within certain predefined boundaries, well, congratulations, your test case ran successfully. Having such known solutions or even expert knowledge to help you with the validation is rather rare, though, unfortunately. So more often than not, you're running test cases without known solutions. And what we do for these test cases is basically following industry best practices, right? We go for the statistical approach and create ensemble runs. And yes, the initial cost to run these ensembles for these reference values is a little bit steep, but once they're in place, they can be reused indefinitely. So I would say it's well worth the initial investment to generate these reference values and the tolerances, of course. Okay, the last point, the metrics. This isn't so much about reproducibility anymore, but just about what kind of metrics you should put into a benchmark, right? And of course, this will differ per benchmark. But for HPCW, the bare minimum that makes sense is to provide the runtime as a bare minimum for the comparison of the test cases afterwards. From that, you can usually already derive a lot of other metrics like simulated years per day or whatever you want, really. But in the interest of easing the comparison, we also have support for the so-called CPMIP metrics, which is a set of standardized metrics originally proposed by the Barcelona Supercomputing Center, if I remember correctly. And yeah, the goal of these metrics is really to serve as a new standard, so to say, for the Earth system models and their comparison. So here we have metrics like core hours per simulated year. You've got a complexity measure, which is based on the number of prognostic variables. And something that is also very nice to have nowadays is at least an estimate of energy usage. Of course, comparing energy usages across different systems right now is a major pain point, which is going to remain troublesome, at least for the next few years. But it's nice to, at least for intra-machine comparison, have such values as well. Yeah, I should also stress that this CPMIP metric support is experimental, but this is also another great example of why you should use such a benchmark suite, or what you could use it for, right? If you have such a project where you have a different set of metrics or something, you can just take all of these applications, throw your metrics at them, and see how they stack up in the real world. Because after all, that's what we've put into HPCW, right? Real applications. So I'm running out of time, so let's quickly talk about a single usage example. I started the talk by introducing the benchmark suite and saying that co-design is a great thing, a great advantage of such a benchmark suite. And as it turns out, we have many different European projects going on right now that are using HPCW. One that I want to highlight right here is the European Processor Initiative, which is developing new processors essentially. And of course, they need some applications to make sure that these new processors are actually better than what we currently have. So here, HPCW is used to test the capabilities of ARM systems and how they stack up to traditional x86. And of course, they're also using it to further improve the compiler tool chains, which are currently LLVM based. A second example we'll skip. And let's summarize everything. So HPCW is a domain-specific benchmark suite for our domain of weather and climate science. I've talked a lot about reproducibility today. If you want to have a chat about the technical stuff or have a look at it yourself, you could do so. The entire project is fully open source, so you can just click this link and yeah, do whatever you want with the project, really. So yeah, that's it. So if you have any questions, I'll gladly answer them.
Let's feel my fastidiousness towards time on presentations made him speed up, but yeah, I don't want people to feel pressure. Yeah. Any questions for him right now? None? I'll ask one, Niclas. So when you have been porting these models to here, you said you use a CMake, SuperMake. Have all the models come with that, or is that something you've had to add in?
So this super build pattern is basically a CMake type of thing. The idea is that you just pull in all of your projects from outside, no matter their build system. And within your project, in this case HPCW, you just build everything and wire everything up afterwards. So you don't have to adjust the models themselves. They exist as they are. We're just pulling them from GitHub, basically, or wherever they are. And then we wire everything up within HPCW. So you don't have to really worry about anything, ultimately.
Other questions? All right. Well, then let's thank Niclas again. And we'll get set for Kameswar Rao Modali. He's a scientific programmer also at DKRZ. He'll be talking today about his work assessing some kilometer scale data sets Interestingly, so Kamesh and I were talking, so DKRZ is up in Hamburg. In Hamburg, the traditional way they all greet each other is moin. So moin, Kamesh. Yeah,
Hi.
it's a correctness and reproducibility workshop, so he can correct my pronunciation as well. So, so I'll let you take it away.
Hi, moin, Brian. So can you hear me? Can you all hear me?
Yes.
Yeah, okay. So, yeah, so today I'll be talking about the developments that are happening here on the kilometer scale Earth system model simulations. So as you can see, it's work represented by many of my colleagues from DKRZ as well as from the next door Max Planck Institute for Meteorology, where the ICON model is actually developed. So mostly, so I'll be talking about what kind of, yeah.
We're losing you're getting really quiet in the room. I don't know if that's on your end or ours. Give us 1 second.
Can you hear? No, you're not able to.
Yeah, thanks.
Yeah, okay. So, yeah, so, yeah. Then, so like I said, yeah, so my colleagues from the Max Planck Institute, like I mentioned, so mostly the infrastructural developments and the modifications in the workflows that needs to be done in order to cater to the kilometer scale simulations. So to begin with, this is the classical Moore's law. Like we have the density of the transistors on the microprocessor is increasing exponentially, and then we have the computational power also increasing proportionally, and finally we are now talking like exascales. So at this point, the interesting question to the system modeling community is like, what is the winning point or something from this huge computational power that we could exploit. So as part of this Warm World project, which is funded by the German Ministry of Research, Technology and then Space Research. So we are addressing some of these questions. So the first part is like, what do we expect? I mean, like, what can happen to the system models? So fundamentally, the system models, because the computational power is not sufficient, so there was a parameterization where the actual discretization could not cater to. And then now with this improved computational power, so this could, some of these parameterizations will be vanishing. And then what kind of simulations can be targeted? If you see traditionally the climate simulations, which are like on a largest global scale, say have been performed and which need for longer duration, were traditionally performed on a coarser resolution because of the computational power constraints. But then now with the huge amount of computational power, so they could the global scale simulations also would be moving close to like kilometer scale. So and then this is one interesting picture from the this textbook. So it represents the spatial and temporal scales, and then the various phenomena that are associated with these length and time scales, and also some of these dotted lines showing the hydrological aspects. And then, as you can see, this is from something around 2011, roughly a decade and a half ago. So, and then at the time, the general circulation models, the system models, was like probably like hundreds of kilometers grid resolution. Now, what we are talking is basically pulling down this to close to the x-axis. So that's what we are talking now. As we saw, there are different gamut of length and time scales which are needed for different scientific pursuits that we saw in the previous plot. So how do we cater to these when we do this kilometer scale simulation? But then someone is interested maybe some other resolution. So how do we try to handle these, and then because the data is so huge, how do we also enable the access of the data for the global audience? Because as these simulations demand huge computational power, and then they could not be they could be performed only at few centers across the globe, and then but then the scientific audience is spread all across the globe. Now, and to address this, we see like the combination of cloud native formats like zarr and then HealPix grids seems to be a plausible solution. So I'll try to give more details about these two in the next slides. So HealPix is like the hierarchical equal area iso latitude pixelation from work of Goski et al. In 2004. So what does this mean? So as you can see in this picture, so at the coarsest level, the globe is divided into 12 base pixels, and then hierarchically we try to divide them further in each generation into 4 children or something from each from the previous generation and so on. And then they have this property that the centers of all of these are on latitude circles, and then they all each pieces in the given generation they have equal area. So this way it enables to match the global phenomena as well as someone who is interested in certain features at a very high resolution. So, and then now in the context of icon model, so how do we rejig our output to fit into this structure? So we are now providing like at 11 zoom levels and then 3 different frequencies. So it's like you have a huge matrix of data sets to say. Each of them is individual zarr store, so which is like like an analysis ready data set. So someone interested in a particular length and time scale, so he can just straight away go to the closest combination of these from this matrix and then just pick his data set without any further interpolation or any other requirement. Now, and then if we look at one of these, one particular such matrix of these zarr stores, so I just tabulated here the sizes as well as the file count. So as you can see, the highest resolution and the frequency is almost like half a petabyte. And then the interesting thing is with the zarr format, the number of files, because we try to store on small chunks because so that they could easily flow through the internet. Then that poses actually a challenge to the HPC infrastructure because you need to do a bookkeeping of a huge number of chunks. And then, in fact, now traditionally HPC centers have constraints on computing node hours and then the disk space, but then slowly there are a restriction on the number of files also is coming into picture. So the next point is like these simulations, when they're performed, initially they reside on the disks, but then as I mentioned, they're already of the scale of a petabyte. They need to move across the storage tiers to make way for the next set of simulations. And then sometimes this process could be, some error prone because as we mentioned, these are like very small size files and huge number. So there could be some, for example, say some chunk is lost or maybe uninitialized or something. So how does it appear? For example, in a given missing chunk or something. So for example, I just took HealPix level 7, and then if suppose one chunk is missing from a time step or something, the thing is because this format is like a fault tolerant format, because if something is missing, it just presumes that it is a NaN value and just you can still generate a plot. And then, for example, in this case, and then, so you see still the information is being visualized. So, and then, for example, at zoom 9, you see as it is a high resolution, each chunk has a less number of information. So it's a much smaller loss. So we need to, how do we ascertain the integrity that all the chunks are in place? So for this, if you look at the typical zarr store, So we have the top level, all the variables. By the way, we are using zarr version 2. So what I'm talking now is relevant in the context of zarr version 2. So in the higher versions, like zarr version 3, some of these problems will be addressed. So, and then, yeah, as you can see at the top level, we have the variables, and then the next level of chunking is at the time dimension. And then, for example, if it is a two-dimensional variable, the next level of chunking is at the spatial dimension to say. And then these are the files. So this is, in fact, one of these chunks that I was replacing in the previous examples that I showed. So then, but the interesting thing is, as all of these are integers, and then it saves us from this problem of identifying these missing chunks. You can just list them and enumerate, and then figure out like, okay, there is some missing information, missing chunk, and then yeah, figure out like if it was already existing in some other storage tier or something like that. So now the next aspect is how do we ascertain the quality of the data. So traditionally, mean squared error has been one of the metric, like for example in image processing also, like when you have two images, so we just try to compare like point to point or something, and then try to find the mean squared error. And then, so now in the context of the simulation. So for example, if we take the starting time step as the reference, and then we can always compute this mean squared error from cell to cell, and then do it across the time steps as well as the pressure levels. So that you get a matrix of the mean squared error. So now the interesting thing is when we try to represent now this matrix plot. So for example, I just took the era 5 geopotential, and then did for all the time steps, taking the first time step in 1968. I just took from 1968 to 2020. And then we see, okay, there is some pattern that we see in the higher levels of the atmosphere, but could be something seasonal. But then, so that it says that, okay, the mean squared error when represented in a matrix plot does carry some kind of pattern or signal or something. So now we switch to, for example, did the same thing for the ozone mixing ratio. And then, interestingly, we see there is some blip that appears somewhere in the top. And then it turns out to be that there is some instrumentation error during that year. So it's like it's interesting. So it increased the curiosity. So then we so similarly we just applied to the model output, and then for example we saw some little bit some streaks that were appearing in the when we do on the daily data. And then yeah, when I discussed with my colleagues, and then it turns out that there was some issue with the synchronization of the daily value computation from the model time step loop. So yeah. And so yeah, so then but we see that mean squared error, yeah, it does show, but then when the errors are more pronounced, it amplifies them and then shows. But then there is no visual intuition or something. Sometimes visually we could find something different, but then mean squared error will not be able to catch it probably in next slide or something I'll be showing. So yeah, so for example, the structural similarity index measure is one from Kwong et al. In 2004. So where they are trying to really quantify the way humans look at two images in terms of the luminance, contrast, and structure. So which is basically the same thing between the two data sets, and then you try to compute from they construct these terms from the mean and standard deviation, the covariance between these two. So more details. So this is the standard image that people who are into image processing might come across. So like I was saying, between the first and second image, even though we just have some noise and visually we see that, okay, there is something blurry or something, but then the mean squared error fails to pick it up. But on the other hand, the structural similarity is able to identify. And then on the other hand, for the third image, if you see, if you just add a constant or something, and then yeah, the mean squared error still refuses to pick it, and then it shows that it says error or something, and then but on the other hand, the structural similarity says that, oh, these two are more closer. So the drawback is like it's humanly impossible or something to create images and then compare for the large volume of data like climate model output. So in this direction, recently there was some modification to the structural similarity index measure by Agarwal et al., who is already in the audience. And then they did some modification to the original form, and then so that basically we are trying to bypass the whole image creation process, and then one could straight away apply this measure on the floating point data itself. Yeah, but then it was applied on regular grids. Like as I mentioned earlier, the idea is to switch to grid forms like Hilpix grids, like unstructured grids, so that we cater to these different length and time scales. So in this direction, so we tried to adapt this the DSSIM, or the data structural similarity index measure, to the Hilpix grids. So for this, we used, so basically the way this is performed is like, as I said in the showed. So it first tries to, tries to create small windows of this image and surrounding each cell, and then tries to fit a Gaussian, and then tries to compare the similar thing in the other image. So the same thing happens even with the floating point data. So the critical aspect is, how do we construct, I mean, because the grid is unstructured. So for the structured grid, yes, your location in the index of the array as well as your lat lon or something is coinciding. But then for the unstructured grid, it's not the case. So we use the Hilpix convolution package developed by the French Institute for Ocean Research. And then so as you can see, I'm just trying to animate the kernel for different cells, for example, just to give a glimpse what we are talking about. And then we made this adaptation, and then finally we implemented, did a small test case, and then so you have your, for example, your reference time step, and then this is the time step that I want to compare, and then yeah, we get some what do you call a measure or a quantity of this visual similarity or something, like, as we can see, yes, the polar region in the top, I mean, like, there's some difference or something. So how do we, so the whole idea is like, how do we quantify this, what we perceive visually? So yeah, so far that's the work that we have done. And then just to summarize, so we are trying to adapt to these kilometer scale simulations, and then that demand like a new way of writing the output, and also a new way of provisioning the data to the users. And then in order to ascertain this data integrity and quality, we need to improvise some things which are counterintuitive to the existing data formats and workflows. So in this way, in this direction, we are adapting, for example, the DSSIM method to the Hilpix grid to almost to reach the level of visual inspection. And for the data integrity, like as I mentioned, we are just using some simple methods like list enumerations techniques. So the outlook is to maybe work further on higher resolutions of this, because this kernel is very sensitive to the, the construction of the kernel is the sensitive part that so far we observed. And then finally to incorporate this into the workflows for high resolution models. So thank you for your attention, and then, yeah, open for questions.
I saw there was some discussion in the chat. I think Deepak and Karsten maybe had a discussion there, so I'll start there if we can pull that up. Let's see. Right. This was on the, so ice.
Yes.
Okay. So not really a question there, just something that you guys are looking into but haven't gotten to yet. Any other questions in the audience right now? I would ask, how complex was it getting the DSIM? I saw you use this convolution tool from the French. Like, was that a difficult effort, or does that work? I mean, do you have a strong preference for the heel picks in this space, or what?
Yeah, actually, yeah, the most critical part is the constructing of this kernel. I mean, like the standard deviation that we mentioned, because in the works so far, it's just like for a given resolution, they were trying to use the DSSIM, but then we have the zoom levels, which are varying on one hand. So, and then, yeah, we need to match the standard deviation of the kernel accordingly to the number of pixels falling in within this. So that has been the challenge. That's what we are currently exploring to make it more robust.
Got it. Thank you very much. Well, let's thank Kamesh again. And up next, let's see if Andrew is here. We have Andrew Kwong. Yep, Andrew's here. So Andrew's an undergraduate student at Cornell. He'll be talking about scientific reproducibility and some regional ocean modeling. He was actually, we were lucky to have him as a SciParks intern this past summer, and we're really excited to hear about the ongoing work with this. So thanks, Andrew. Take it away.
Yeah, awesome. Great to at least be here online. And I'm just going to be sharing some work that I did this summer with my SciParks project on enhancing scientific reproducibility and CrocoDash for regional ocean modeling. And let me go ahead and share my screen real quick. There we go. All right. And so, yeah, enhancing scientific reproducibility and CrocoDash for regional ocean modeling. And yeah, my mentors worked with Manish up here and Dan. So regional ocean models are powerful tools. They allow us, they provide some numerical representation of the processes with these models. And so by allowing us to understand physical and biogeochemical processes that often otherwise go unresolved in global climate models, we have something very powerful in our hands. With that said, it can be quite time consuming to set these regional ocean models up. So with the technical overhead that's involved, this is pretty much where the CrocoDash project comes in. And so with CrocoDash, right, we're trying to accelerate regional ocean model setups in CESM so that we're able to set up these models from months and weeks down to days, and preferably even just hours. So right here, we have an animation depicting sea surface velocities over the Northwest Atlantic. So right, as I've already stated, these are some very powerful tools that we can be using. So my goal is to enhance scientific reproducibility and increase accessibility in the CrocoDash workflow. So CrocoDash is our user-facing Python package that allows users to set up regional MOM6 cases. And I want to have this fully reproducible end-to-end workflow where users can create these regional MOM6 cases. So right, we have our case, our domain. We're dealing with specifically horizontal grids, vertical grids, bathymetry data as well in our regional ocean model. These different things that we have to contend with when setting up our domain. And also our forcings from initial conditions, open boundary conditions, tides, and chlorophyll, as well as some other factors that we have recently been added into CrocoDash as well. So yeah, with our workflow in CrocoDash, right, our first step is going to be generating a domain. We then create a case. After this, we prepare ocean forcing data, and then finally, we are ready to build and run a case. So we have model setups that are a lot more user-friendly and streamlined in this workflow, but there is still a lack of reproducible features in CrocoDash. So in order to sort of get at this idea of being able to add reproducibility into CrocoDash, what I mean by this is, right, if we take a look at what the workflow looked like in one of the Juniper notebooks that uses this workflow from before I came in this summer, is that we had these features with our tuple editor, sort of a interactive tool that users can use to edit bathymetry data in setting up a domain for a regional ocean model, as well as these steps to generate a horizontal and vertical grid. And as you can see, there isn't much in the way of interactivity. And especially in the tuple editor, which we can see here, there is no way for us to save our state. So whenever we make edits in our topography, and of course, this can be a very time-consuming process, there is no way for us to track these changes across sessions. And so this is what I'm really trying to get at is, how can we add reproducibility to this workflow? So I've mentioned reproducibility quite a few times, and ultimately what I had in mind when working with this project is, how can I implement something that's ultimately repeatable, traceable, and transparent? And so as I've alluded to already, editing topography can be quite time consuming, and there's a lot of tuning involved. So when we take a look at this sort of refactored tuple editor, where I've been able to make some changes to this tool, is that when we look at this domain over the Outer Banks, Chesapeake Bay, so yeah, looking at the Mid-Atlantic East Coast region, we can see that ultimately the reason why we want to be able to have this reproducibility, especially with regards to the tuple editor, is that, right, when we're making these edits to our bathymetry, and we're smoothing and deepening or reshaping data so that we make changes ultimately so our regional ocean model doesn't blow up, is that we can ultimately get to something where we can tune our model, go back and ensure that whatever changes we make are tracked and traced and ultimately transparent, so that when we can go back, we don't really have to worry about not knowing like what changes that we've made over time. And ultimately being able to go back and make refinements in this process of model tuning is what this is all about. And so I've been able to go in, add some features of reproducibility, which I'll talk about more, including history, version control, and shareability. So the first feature, which gets into history and provenance. So I have this little demo that I created in the tuple editor. Just as a quick disclaimer, these are very unrealistic edits that would actually be made. But just to show what's going on, we can see that the user is making a few edits to our topography, so including a change to the minimum depth. There's some features as well where you can erase disconnected basins as well. And once you're ready, once we're happy with the changes that we've made to the tuple editor, you can provide a name and a message to the changes that have been made. And so with that, we can now click the Save State button. And what this does is that we've now saved a snapshot of the topography and the edits that we've made. Similarly, with the Save State button comes along with it the ability to load in previous states as well. So by having this log of the changes that we've made in the tuple editor, we can load in previous snapshots as well. So now you can see that the user's now loading in the original snapshot. So, right, this is what the domain looked like before any user edits were made. If we go back to the medium depth East Coast snapshot, in which the minimum depth was set at 5 meters, we can click undo and redo accordingly. Right, we click undo and we can get back to the original topography. So just to reiterate, with this new tuple editor edit history section, users are now able to save and load snapshots across sessions with this new history log of modifications. So now that I have a history to log changes over time, my sights are now set on integrating some form of version control. And really, sort of the basic idea was just using Git to handle commits, branches, and checkouts, in the topo editor. So as you can see on the right, we have these new features where users can create and delete branches, check out, and merge as well. And overall, this promotes data provenance and traceability. And this is important because it's conducive to experimental workflows, especially when we're making a lot of these fine edits in the topo editor and going through this process of tuning. We don't have to worry necessarily as much about making destructive edits in the topo editor because we can now obviously go back to previous states. In addition, users can also share topo and grid configurations through Git repositories. And so I'll show you what this looks like in terms of the workflow and setting up a domain for a regional ocean model. So our first step really is generating our horizontal grid. And so with this, I've already talked about the topo or topography, but when we look at our horizontal grid, there are actually 2 additional configurators that I ended up creating, including something called the grid creator as well as the vgrid creator. And so with this, the user can create additional horizontal grids for a regional ocean model if they want to make some fine tuning. Once we've instantiated a grid object, this is then fed in to generate our topo object. And I've already mentioned that we can make customizations to our topography using the topo editor. Finally, our last object that's involved, our vertical grid. Similarly, after we generate our vertical grid, we can create new vertical grids using this vgrid creator. And these 3 objects are then used to instantiate a case object. And from there, we can build and run our case for simulations in a regional ocean model. What I really want to emphasize in this sort of diagram right here is that topos are located in Git repositories. So what I mean by this is whenever we instantiate a new topo object, we are essentially under the hood initializing a Git repository as well. And in this Git repository, it's going to contain an associated horizontal grid object that was used to instantiate our topography. And then on the other hand, with our grids and our vgrids, so this is, of course, still accessible to the user, but they aren't necessarily going to be located in Git repositories. And the main reason being is that whenever we're sort of making customizations to our horizontal grid and vertical grid, we're actually just creating new grids altogether. Whereas with our topography, we're actually mutating the object itself. So I've talked a lot about the topo editor already, and I've mentioned the grid creator and vgrid creator. So when we take a look at this grid creator, sort of, how can I add interactivity into the workflow and making it easier for users to create a grid that they want to. So as you can see here, I've added sliders quite similar to what we saw in the topo editor, where users can essentially be able to create a horizontal grid with this new features based on our resolution and as well as our lat and lon. And so once you are happy with the changes that we've made, we can provide a name and a message and save and load grids from our grid library. And we have a very similar story going on in our vgrid creator as well. So with our parameters, right, with our vertical grid in a regional ocean model, we're sort of concerned about resolving processes in the sort of towards the ocean surface where there are more spurious flows going on. And so with this going on, we can provide a name and a message as well as save and load grids, vertical grids from our vgrid library. So this is great and all. I've essentially been able, with the changes that I made up to this point, create a workflow that is a lot more reproducible in the way of generating a domain for a regional ocean model. And so in terms of tying this all together, how could I make this workflow end-to-end reproducible? And so with that, my last step was really just adding reproducibility to the preparation of forcing data, which really just involved saving a history of the configurations when creating a case, saving this to a JSON file. And so having all the previous configurations from all the cases that have been previously created saved to a JSON file. So as you can see here, the user is selecting these different domain objects from the different histories that we have from our vertical grid and horizontal grid libraries, as well as our topography topo repository as well. And so now with what we can see here, we can select a forcing configuration that we've previously made from a previous case. And once we've selected that, we can provide a name for our new case. And so really what this is doing is sort of assembling a whole bunch of different pieces from different parts of cases that we've already made beforehand. So we're not really doing anything new here in terms of generating new objects, but it makes it a lot easier for us to be able to pull things together, especially with how modular it is in terms of setting up our domain. And so once we run, click the generate forcings button and allow it to run for a few minutes, what we get is something. So we've added parameter changes to our forcing configuration file, and we can see that the case is ready to be built. And so what this is it's really powerful in the way of us being able to have something that's fully reproducible end to end. We didn't have to do anything, like any new work for us when assembling this new case. So really what I was able to pick up from this summer was really just sort of the importance of reproducibility, and really that it requires intention and infrastructure. And sort of when I came into this, I sort of didn't have really a clear picture as to what that entailed, especially when working with regional ocean model. But by working in the CrocoDash workflow and being able to implement these features, it really allowed me to understand that a lot of this is really core to the workflow, and how users are able to create these new regional ocean models, these new cases. It's really central for us to be able to incorporate reproducibility. Another part is that modular design enables reusable modeling. And I didn't really get into this as much, but really with how the workflow is set up, right, with setting up our domain, by having established some form of reproducibility and creating our horizontal and vertical grids, and adding reproducibility to customizing our topography, by adding that all together and sort of combining it, we were able to get at this case assembler, where we could essentially assemble different parts that individually were reproducible. And that's what I found to be very much powerful. And finally, good science begins with reproducibility. And very much so in terms of the philosophy as to what does it mean for us to conduct good science. And I think for us, it's really important, especially in the context of open collaborative science, that we're able to have known the changes that we've made. And by tracking what we do, we're able to preserve why results matter. And so with the work that I did with my mentors, integrating these modular configurators, incorporating version control editing and reproducible tools, we laid the foundation for rapid reproducible Earth system modeling. And so with additional work, a lot of this after the bulk of my internship was done after this summer, is really just going in and adding in documentation, especially into the Jupyter notebooks, especially for the workshop that recently happened with Crocodile. And then of course testing, which really my project sort of was originally like half and half between software correctness and reproducibility. It just so happens that I really leaned into the reproducibility side of things. And then of course, extending features, that's something that that's still planned on being done, is handling for other grid and edit types. So really all of the work that's been done up to this point has been in the context of rectilinear grids. And finally, adding to the reproducibility suite. So of course, we've been able to add in chlorophyll, and then also BGC, and then runoff as well. So being able to add reproducibility to those components as well is sort of the next steps in the CrocoDash workflow. And yeah, here are my acknowledgements. Of course, I have great thanks to my mentors, Dan, Manish, and Alper, and then of course to SciParks as well as the National Science Foundation and NCAR, of course. Happy to take any questions.
Any questions for Andrew? Yeah, Eric.
So Andrew, this is great work. I'm really interested in this. I'm interested in the link to Git that you did. So it creates a repository in, we do something similar in CSM as a whole for cases. And I was wondering if you leverage that or if it's a different Git repository. And tell me more about the Git part of this.
Yeah, so it's not connected to that your Git repository. Yeah.
Okay, and then does it make a local one that you can then
Yes.
upload if you want to, anything?
Yeah, that's the main idea. And so, especially with some of the objects and especially with some of them being quite large in size, not everything's going to be handled through the repository. And so, some of it's going to be handled through like LDS. So.
Okay, cool.
I'll also add my favorite thing about this is, you know, there's reproducibility and then there's easy reproducibility. The user interface aspect of this is really nice. Right. So, yeah. I'm going to ask you one loaded question, Andrew. I take it you enjoyed your time as a SciParks intern?
I did. Actually, yeah, it's really funny because one of my professors was sort of advertising the SciParks internship. He sent out an email to sort of the department today, and so I was like, you know, I am front and center going to be here to like say good things about the SciParks internship, and yeah, it's a really good experience.
And that's why I asked. So literally just yesterday, the announcements went out for next year's SciParks, next summer's SciParks.
Yeah.
So undergrads, graduates, there's ones for both. Speak to Sam or speak to me, and yeah, we're happy to get you information. So great. Let's thank Andrew again.
You said no.
Well, then I would have said something different. Yeah.
A couple of quick things. So, one, before I forget, end of next week, you should be getting a survey about the meeting, and I really would ask you to please fill it out in person, online, folks, to let us know your thoughts and comments. The second thing is we have one more session this afternoon with 3 more great speakers. We will reconvene at 1:20, so you have a little bit longer for lunch today. And I think I said this yesterday, but today lunch is provided for you. You don't have to pay. So go down to the cafeteria, go to that east end where we've been before, and everything is laid out.
Yes.
Yes.
It's actually open right now, just
good.
because the catering staff thought we might need more.
Oh,
But it
okay.
is all set up.
It's all set up and it should be labeled, I believe. We covered everyone's dietary requests, vegan, vegetarian, meat.
Carnivore.
Gluten-free. Anyway, so if you requested something, hopefully you go down there and grab it before someone else does. No. Okay, all right, thank you. See you back at 1:20.
And then just hook that in.
Hook this in my pocket?
Yeah.
Okay.
Oh, yeah, just actually for the share.
I really do. I don't have.
Hello, everyone. Welcome to the afternoon session. This is the last session of this workshop. So we have a lineup of 3 exciting talks in this session. And the first talk is characterizing and correcting non-standard arithmetic in GPUs for scientific computing. And Paul, please feel free to.
Hello, I'm Paul. I'm from Purdue University. I'm an undergraduate senior studying computer science. And I did this work under Ganesh here. Yeah, and Benjamin Valpi from Rochester University. Sorry. And what we did here is, so GPUs, they're all the rage right now. As we saw recently, NVIDIA, by selling these GPUs, reached $5 trillion in market cap for temporarily, until recently. And they're very useful for a lot of different workloads, and they're very useful for, sorry. Like I manually click it, sorry. They're very useful for all of modern AI. We cannot carry out these large computations without them. And they're also very useful for a lot of scientific computing too, for some variations of GPUs. But a recent advancement, well, not recent, but within the last 5 to 10 years, one of the magics that make these GPUs work that like they do is the specialized units within them called matrix accelerators. So with AMD, they're called matrix cores. With NVIDIA, they're called tensor cores. We specifically in this talk discuss tensor cores as, I guess, a specialized unit that performs matrix operations of the form D is equal to A times B plus C within a block. So it's a block fused, like multiply, add, accumulate. So block FMA. And until recently, the precise semantics of these units were proprietary and effectively a black box. Basically, NVIDIA, they likely did not want people, again, we don't know, but allegedly they did not want people to know how they worked. So it was only through recent work that, in the last 5 years, that researchers in this field were able to kind of reverse engineer how these architectures and exactly what they do to perform these computations so quickly. So through the recent work of Fossey, Lee, Mantis, and Valpy, we were able to finally get a precise specification of like the semantics of exactly how these GPUs function, how these accelerators function, and what they do to perform arithmetic. And what they do is very IEEE non-standard, well, because they have to cut corners for efficiency. So sometimes just understanding the semantics is not enough, especially if the behavior of the architecture can introduce errors. So early work by Fossey and Mantis demonstrated that the semantics is, the non-standard behavior of tensor cores can lead to something called non-monotonicity. And non-monotonicity in this context, I'll define the next slide, but it can violate a lot of basic assumptions in numerically sensitive code, which affect convergence, error bound stability, things like triangular inequality it could not hold. So consider an addition of 3 terms. We have 1 plus 2 plus 8. This, in real arithmetic, you would generally assume to be equal to 11, right? And then consider a second addition where one of the add-ins is larger, 1 plus 2 plus 9. And this would generally be assumed to be equal to 12. In the case of non-monotonicity, like if we assume that some adder is non-monotonic, and it is possible for the operand to decrease even if an add-in increases. So in this case, it is possible under specific situations for, say, an adder to have 1 plus 2 plus 9 be less than 1 plus 2 plus 8. And this can be quite bad for a lot of, well, situations, because we don't exactly, we want math to work how it works. So often, tensor cores and a lot of these GPUs and modern matrix accelerators are good enough for machine learning, but they're not good enough for scientific computing, which makes sense because we want math that works. So the motivation behind this is the internal arithmetic of these accelerators, they also evolve with each generation. So far, we do have work that has formalized the semantics of how these units work, right? How they perform their operations. But with each new GPU that NVIDIA comes out, they also come out with sometimes a new specification of tensor cores. So recently, that was the Blackwell GPU. And with each generation, these tensor cores actually operate slightly differently. So it's important to formalize the precise conditions under which some of these emergent behaviors inherent to like the architecture of tensor cores, how they occur, in an effort to understand the input ranges that may trigger this behavior, and also to help inform hardware designers for future generations when they do innovate and like upon these to ensure that these behaviors that emerge from likely the architecture itself are guarded against. So basically, we want to find out exactly how can we design these while keeping their advantages to ensure that this bad stuff cannot happen. So I'm just gonna go over some preliminaries. A lot of you guys may be familiar with this, but this is just basic like floating point syntax. So generally floating point, it consists of a sign that's either 0 or 1, sign bit. It consists of an implicit bit 1 point and followed by m bits of mantissa, which is, and then times a value 2 to the, it has e bits of exponent. I'm just going to ignore all bias for this context if that's a question. But and then UOP, unit in the last place, is often termed the value of the mantissa's least significant bit if it is set. So it's a position, the power of 2, of the lowest possible bit that can be set in a floating point terms mantissa. So generally, and this is an example of not a real precision, like floating point precision. This is just an example of what it looked like. We'd have a sign bit here. We'd have an exponent. This is, I had it in base 10 because it'd be a lot simpler to put this way. We have an implicit bit, and then we have a mantissa. This mantissa would only be 5 bits. We will only be using 5 bits for the examples in this talk, but generally with single precision, it will be 23 bits. Half precision, it will be 10 bits, and then 11 bits with the implicit bit. And then tensor cores generally vary generation by generation in 2 ways. They vary, one, by the number of terms that are added in a single block. So they perform what is called block FMA, block fuse multiply accumulate. And so they perform a set of A times B multiplications, and then they accumulate all of these into a C term. So the number of A times B terms that they accumulate in one single block changes by generation. And also they append, and this is very non-standard, but they append to the end of the mantissa an extra P number of padding bits. So generally in IEEE standard, say like round to nearest arithmetic, they have 3 extra bits at the end of the mantissa to round it. They have something called a guard bit, a round bit, and a sticky bit. So tensor cores, they get rid of all of this, and they just have a set number of just bit positions. They do not have any special function besides just being there for additional precision. So this is a table of the existing architectures. I did not include Blackwell in here, but of Volta, Turing, Ampere, and Hopper, where Volta, they have a block size of 5, so they multiply 4 terms, A times B, A times B, A times C, A times C. So there's 4 terms that they add, and they add these 4 terms into a single C term, which is the 5th term. And with Turing, there's 5, Ampere, there's 9, and Hopper, there is 17. So we notice that all of these are quite different. And you'll see in a bit that it can lead to some pretty different results too. So how exactly does a tensor core work? A tensor core performs its operations in 4 primary steps. So the A-B terms are computed exactly and held in FP32 generally. Tensor cores do generally also have an FP64 format, but this is less interesting because they do things that do not exhibit this behavior. And we want fast arithmetic, we want lower precision. That's just how it goes. And then it's going to be exact because, so how tensor cores work is they multiply half precision, or say FP16, BF16, things where the mantissa is significantly lower, and they multiply these 2 terms into an FP32 output, right? So the mantissas of 2 FP16 terms or 2 BF16 terms can fit exactly within the size of the mantissa, or the number of bits in the mantissa for single precision, which is 23. And then afterwards, so assume that we just have, say, in the case of Turing, we have 5 terms now. We align all of these terms to a single, to the maximum exponent of all these terms at once. So generally in IEEE standard floating point arithmetic, we align these terms, we only add 2 terms at a time. So this is an n term adder, and we align it to the largest term. So this is the same thing, but we're doing all n terms at once. And then the line significants are all summed at a single time within this extended significand with the extra p bits of padding. And the results are normalized, and the bits beyond the mantissa, instead of being rounded, are actually just truncated and lost. So even bits that are in the padding bits at this point in time would just be lost. So we're losing a lot of precision here. So I'm going to run through a quick example. I hope I'm not too much time here. But basically, imagine that we have this imaginary precision where we have 5 mantissa bits, just for simplicity, right? and 1 padding bit. And we're adding 4 terms here. So we have these 4 terms. We want to, in the first step, and we're ignoring the AB multiplication because we know this is exact. In the first step, we see that the max exponent is 20. So we want to align all of these terms to 20. And we see that a decent chunk of the bits are shifted out into the padding bits and into the lost bits. These lost bits are immediately lost. They're gone. We do not keep track of them anymore. So all this precision is, at this point, it's already gone. So we get rid of them. And then at this point, the adder, it adds these 4 terms together, which we see here. We get the sum. We get this sum, which is unnormalized. So then we have to perform another normalization to get the implicit bit alone and all the rest of the bits into the mantissa, at which point we shift the 1s out into the padding and the lost, and both of these bits at this point are now dropped as well. So if you guys saw in that example, we lost quite a large number of bits throughout this process. And again, this is okay for tensor cores, but we do not want this for, this is okay for machine learning workloads, but we do not want this for scientific computing. In most cases, I would assume. So now that we know how these units work, let's try to investigate a case of non-monotonicity. So this was originally brought up in a paper by Fossey in 2020. It was the first work on kind of trying to identify how these adders exactly functioned, right? And the example he gave, this is a similar example, just at reduced precision, is that given 4 terms, right? 4 or more terms, you have the ability of, when you shift, so we see that there's a max exponent of 24. When we shift, we actually shift all the bits out into the lost bits. So basically all these bits are lost. It's as if we're adding 0 to this top term. Okay, they're gone. Now we add, and we see that the output is the exact same as the largest term, so we have no change at all throughout this operation, right? But what if we subtract this largest term by the smallest amount? So we subtract this by what is called 1 ULP, which is defined earlier, which is, this is just the next lowest representable value in floating point at this precision. And then what if we add these exact same terms again? We align them, and we see that they're actually representable again now in the lowermost bit of the mantissa of the largest term. So when we add these, we actually get, these terms actually contribute to the sum, sorry. And at which point we get a carryout term, and then we have to renormalize. And we see that this sum is actually larger than the sum that we just saw, where we had a larger term that was adding these exact same smaller terms. So typically, by the literature, this is described to be resulting from a class of adders that compute n terms, the sum of n terms without normalization. So generally in IEEE standard adders, monotonicity is ensured because after each 2 additions, they normalize and they add to a next term. And it's also why the order of operations matters a lot in floating point. With this, since we're adding all these terms at once, and we only normalize at one point, it's a lot faster, but we can introduce phenomena like this. So this kind of leads to the question, like, is there a space within this class of adders that is guaranteed to be safe from non-monotonicity, while also keeping what makes tensor cores efficient, this single step adding and normalizing a rounding operation or truncating operation, right? So can we leverage what makes it fast, and can we also get rid of what makes it unpredictable? So the intuition is, we can see from the example just given now, is that when we have a large term and we have n-1 smaller terms, when the large term's exponent decreases, the smaller terms can re-enter the representable range of the large term, right? We saw that the bits that originally aligned in the lost bits actually shifted back into the bits that were representable in the mantissa of the larger term once it decreased. So non-monotonic behavior in this case occurs in a tensor core accumulator if the sum of the smaller terms that come back into the accumulator are greater than the decrease in the larger term. So without loss of generality, let's assume the larger term is T1. So T1 minus T1 prime has to be smaller, smaller than the sum of the terms that can now suddenly become representable in the mantissa of the larger term. intuition again. So basically a tensor core accumulator is n plus p bits wide, right? So we have the mantissa bits, which is for any floating point format, and then we have p bits, which is inherent to the tensor cores and how they add, which is the extra bits of precision that appended to the end of the mantissa. So this means basically the more padding bits that we have, the smaller the terms have to not be representable in the larger term, right? Because if we have a larger term and it shifts into the padding bits, it's still being summed and potentially contributing into the larger term prior to say T1 instead of like T prime, right? So we want to shift out of the padding bits of this T1 as well. And then be within these bits for T prime. And if we want this flow back to be larger than the difference between these two terms, they want to maximize the amount of how large these smaller terms can be. So let's look at an example with n equals 4 and we have one padding bit. We align to the largest exponent, which is 24. And then we perform these sums. And you see that when we align to 24, now they fall within the padding bit and they can suddenly be added. And we drop this, we truncate the term in the padding bit, and this is our final sum. Now, if we do this and we decrease it by one ULP, then we do the same operation, and we end up getting the same sum. So it's no longer monotonic in this case, right? But this is just for one example. So how can we know that for all examples, if there is some way or some space within these adders or this class of adders that we can ensure monotonicity? So this is a theme that we kind of came across several times in the last few days is SMT solving, SMT solvers. So SMT solvers can be powerful in modeling arithmetic schemes. Z3 and CVC5, they have what is called bit blasting. Is in, say, an array of a bit vector, it's just an array of bits. Each bit is a single variable. And basically, it just adds constraints on each of these individual bits. It can be very compute heavy, but it's very good at reasoning about bit operations. So we can see we model how tensor core works in SMT. We align n terms, we accumulate with p extra bits, we normalize and we truncate, and then we add these assertions. We can feed it into SMT solver and we can see, okay, can this happen or can it not happen? And in this case, we can assert whether non-monotonicity can happen or not. So the intuition that we came up with before was basically the greater the p, the less likely monotonic, the more likely monotonic, the less likely non-monotonic, because the smaller terms are smaller now to be shifted out of the mantissa and p, or the representable bits of the larger term. And then the greater the n, the more terms that are being added to overcome this difference in p minus p prime. I mean, T1 minus T prime, as termed before, is now larger if we are adding more small terms. So for each n, that n is, say, some 2 to the k plus 1. So this is how, is that out of time?
Maybe a minute.
Okay, a minute. Okay, I'll just, this is here for anyone wants to see. I'll skip over it, but then here are the results. So basically we can see that there is definitely a very clear boundary between the adders that can be monotonic and the adders that cannot be monotonic. I mean, the adders that can be non-monotonic and the adders that cannot be non-monotonic. And then this is just a heat map. I'll go over it if anyone is interested. It's there about how the extent of how large non-monotonicity can get for these ones that can be non-monotonic. And basically, with the existing architectures, actually all but one architecture is susceptible to this non-monotonicity. So they have these cases where it's possible that we can have adding a larger term can decrease the sum. And this is, sorry, I'm rushing, the precise formula that tells you, okay, whether a combination of adding n terms with p padding bits can give you non-monotonicity in an adder. This is derived from the data. I have a proof here. And then main takeaways here. So yes, there is a space of hardware configurations that fall within this class of tensor core-like adders that do not allow for non-monotonicity. The existing Turing architecture falls under this classification. And then we have only discussed non-monotonicity here. What about larger bounds of general error that come inherent to tensor cores? Is there a way that we can ensure correct rounding or some sort of correction scheme for these two? If you're interested, come talk to me, we can discuss. Thank you. And then here is a hand-derived proof for saying like when can an adder be non-monotonic. Okay.
So in interest of time, maybe get one question. Anybody? Any question from the audience? Or from online? So I have just one question. So so do these tensor cores always are turned on for scientific whenever we use GPUs, or are they only turned on for like when there is a compute intensity or something like that?
So it's when you call a certain operation this matrix multiply operation, right? So generally you can call it like SIMT cores and GPUs that perform IEEE standard like arithmetic. But then there are these units within GPUs that are called matrix accelerators. So they are not the GPUs themselves, they're a unit within the GPU that you can call.
Okay, yeah, thank you. Thank you. So our next speaker is online. The talk is a short history of artificial intelligence and what it can teach us by Anissa.
Hello, can you hear me?
Yeah.
Great. All right, so hello folks. Good afternoon. My name is Anissa and I'm here to give a talk called A Brief History of Artificial Intelligence and What It Can Teach Us. So up front, I want to make clear what this talk will not be. First, this talk will not be comprehensive or exhaustive. Heavy emphasis on brief and brief history here. There were so many things that I had to cut from this presentation. And at the end of the presentation, I'm going to have some supplemental material and further reading that I had to cut, but I couldn't fully leave out. Also, I'm not going to pretend to be unopinionated in this talk. I'm not aiming to shy away from having a distinct perspective on the topics I'm covering here today. And by the end, I'm pretty sure you'll know what those opinions are. So the way I came to making this talk was by starting with a pretty basic question. What are we talking about when we talk about AI? I'm sure, like all of you, I've been in conversations, possibly in this very workshop, where AI has meant an umbrella, a variety of different things, and that may have caused some confusion. Commercial products like ChatGPT and more traditional machine learning techniques are two distinct things, but are both discussed vaguely under an AI umbrella. And this made me wonder, what was AI originally? Why do we call both of these things AI? And how exactly did we get to where we are in this AI conversation? So once again, I want to emphasize that this is brief and non-exhaustive, largely limited by what I could reasonably fit onto these slides. This timeline, in my perspective, represents a meaningful subset of a history of AI achievements, roughly from the 1956 Dartmouth Conference, where the term AI was coined, up until the release of ChatGPT 3 in 2020. I'm going to assume that we're all generally familiar with the broad strokes of achievements after 2020, and for the sake of all of our sanity, kind of just leave that out and count that as the beginning of our current AI age. But going back to 1956, the term AI is considered to have been coined by a man named John McCarthy. He, along with others, proposed a, quote, 2-month, 10-man study of artificial intelligence to be carried out in the summer of 1956. The study would, again, quote, basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. Whether or not this was a rational proposal or something that has come to be seen outside of the topic of this talk here. But anyway, in 1956 saw the release of the Mark I perceptron, a giant machine that could differentiate between sheets of paper held in front of it based on whether they had a mark on the left or right side. 1965, Eliza, which was an early chatbot that would rephrase the user's questions back to them in the style of a Freudian therapist. Jabberwacky, another early chatbot in 1988. This one was made primarily for entertainment, and later, if you're familiar, became cleverbot.com. Also in 1988, a paper called a statistical approach to language translation marks a shift in AI research from manipulating symbolic representations to a more familiar probabilistic approach. In 1997, IBM Deep Blue beats reigning world chess champion Garry Kasparov in a 6-game match. 2011, Siri, also 2011, IBM Watson competed and won at Jeopardy. Many other things that could be added to this timeline. But something else that I want to add to this timeline is more than just AI accomplishments. When I looked back to see what AI started as and what it has come to become, I saw that AI has received broad criticisms right from the start that echo a lot of the conversations that I find we're having today. Going back to the Dartmouth conference, contemporary accounts suggest that the term artificial intelligence was chosen mostly to differentiate the field from cybernetics, and some prominent kind of unruly figures in that field, and not to define a distinct field. It has also been argued that the term AI stuck as firmly as it did due to its ability to secure funding from the newly formed DARPA and not to any inherent merit over similar fields, which might feel familiar to some of us in the room today. In 1973, Sir James Lighthill was asked by the British government to evaluate the state of research in British artificial intelligence. The report was largely critical and is thought to have contributed to a decrease in funding for the field, contributing to AI winter or winters, depending on who you ask, somewhere between 1970 and 1990. From this report, quote, most workers in AI research and in some related fields confess to a profound feeling of disappointment in what has been achieved in the past 25 years. Workers entering the field around 1950 and even around 1960 with high hopes that are very far from having been realized in 1972. In no part of the field have the discoveries been made so far produced the major impact that was then promised. Another prominent AI critic was Hubert Dreyfus. While his critiques were taken less seriously, I find it interesting to see echoes of his current AI criticism reflected in his work. He wrote a short paper called Alchemy and Artificial Intelligence in 1965, which he later expanded into a book called What Computers Can't Do, published in 1971 by the MIT Press. From a very good book that I think everybody should read, Pamela McCorduck's Machines Who Think. It is the point of Dreyfus's book that human and artificial intelligence are in fact quite different. In particular, that human intelligence is unique. Not only that, but great misunderstandings account for public confusion about thinking machines, a misunderstanding perpetrated by unrealistic claims researchers in AI have been making, claims that other thinking machines are already here, or at any rate, just around the corner. There was actually a third iteration of this called What Computers Still Can't Do, published in 1992, and I appreciate that incredibly petty academic title. In this piece, he says, no piece of equipment makes sense by itself. What makes an object a chair is its function, and what makes possible its role as equipment for sitting is its place in a total practical context. This presupposes a certain fact about human beings, fatigue, the way the body bends, and a network of other culturally determined equipment, tables, floors, lamps, and skills, eating, writing, going to conferences, giving lectures, etc. Even the perceptron from our original timeline was considered too speculative, and it was excluded from a collection of influential AI papers called Computers and Thought by Edward Feinbaum. Later, speaking with Pamela McCorduck, again for Machines Who Think, he said, AI is hard to define anyway. Most of the time, it ends up being viewed as those things which the AI people are doing. Anyway, I don't know if maybe this was just me being ignorant of this particular history, but I was rather surprised by the prescience of these arguments that were made decades ago that still feel incredibly relevant to our current day. Coming back around to the AI of today and what I promised, what we can take from all of this in our modern conversations about verifiable AI and reproducibility. The AI from today, like Dreyfus said about a chair, comes from somewhere and is a part of a larger evolving conversation. It feels like AI in the past 5-ish years has been something genuinely new. And while aspects of scale and maybe efficiency are certainly new, we can see reflections of this time repeated all the way back to the very beginnings of AI as a field by itself. I want to take a moment to pull out a couple of specific considerations and recommendations for the current day based on everything we just saw in the timeline. In conversations about correctness and reproducibility elsewhere, I want to come back to what do we mean when we talk about AI, the question that kind of started this presentation for me. I think it's become increasingly necessary to become precise with our language around these products, tools, methods. Separating out generative AI products, specifically things that are products and services run for profit for people today, from machine learning techniques and whatever might be considered artificial general intelligence, which again, not touching at all. But I believe not just clarifying for conversations, but materially important to conversations about correctness, reproducibility, and verifiability. As the correctness, reproducibility, and verifiability of these categories of AI is vastly different. And by referencing all of these things under a general umbrella of AI, I believe that we lend verifiable credibility across to unverifiable generative AI products. Additionally, I believe it is important to restrict the use of anthropomorphizing terms. I'm far from the first person to say this, but by referencing LLM's incorrect responses as hallucinations, I believe that this sidesteps the reality that LLMs are inanimate programs that are not intrinsically concerned with correctness as much as they are gigantic statistical machines that piece together statistically likely sounding words into responses to queries, which leads nicely into my next point, which is acknowledging limitations. In addition to being precise with our language choices, I think it is important that if you're developing AI tooling, for example, if a coworker might use an AI tool that you are developing, that it is necessary for whatever documentation provided to be able to quickly and easily determine its limitations based on that documentation right up front. Is your product, for example, an ensemble member that tends to overestimate sea surface temperature, or are you using generative AI to infill time steps in a messy data set? Or is your project something more like deploying a proprietary LLM-based documentation chatbot? All of these products could be called, or all these projects could be called AI in some capacity, but the specific risks involved for each of them has vastly different implications. I also want to add a point here, which is a bit reductive, but I had to put in here somehow. LLMs and generative AI products are not reproducible or verifiable. They're often not correct either. I know this is reductive, but as I mentioned before, LLMs are not and cannot be designed with correctness in mind. When LLMs return a correct response, it is because humans often write correct information on the internet or have it uploaded to the internet in some capacity. And that has been used to create, again, an incomprehensibly large but not magical statistic machine that can spit it back out to us. I don't remember where I heard this originally, and I'm not the first one to make this comparison, but LLMs as they currently exist are kind of like the infinite typewriters in Infinite Monkeys. Instead of having to wait for infinity to produce something resembling Shakespeare, they've been trained on a truckload of GPU hours to statistically give us something that sounds correct or that sounds plausible to our query. Our original monkeys don't know Shakespeare, and LLMs don't know anything either. The next consideration that I wanted to address was objectivity bias. If a machine makes a decision, is it more objective? For example, I've seen suggestions to use generative AI products to reduce bias in performance reviews or to screen job applicants, even from like internally at NCAR. As Dreyfus said, no piece of equipment makes sense by itself. Everything exists in some context. Whether it's a set of observations that are more sparse over the global south being fed into a machine learning model, or LLMs trained on the worst corners of the internet, whatever biases exist in materials fed into these products, both generative and machine learning, can and will be reproduced on the other side. Finally, as AI finds its way into more projects and funding proposals and conversations, I want to specifically address the concern of inevitability. I believe that you can see, maybe hopefully from this timeline presentation, that we've been at a similar point before in the 1960s, 70s, and maybe again in the 80s and 90s. During prior AI booms, I'm sure AI may have felt similarly inevitable, and I've often heard the inevitability being talked about in current conversations. Do I think that the products that have become available in the last 5 years will ever fully disappear? No, probably not. But the question of inevitability, I think, is more about the inevitability to our specific field. As in the 60s and 70s, I think it is far more likely to fade in importance as funding and public interest shifts. And by framing AI in all its forms, but generative AI specifically, as inevitable, what possibilities are we ruling out? What are we not working on in pursuit of AI instead? What products or other methodologies do we not allow ourselves to consider rejecting when evaluating their inherent usefulness other than generative AI? Yeah, that's it. Thank you all for listening to my AI rant. I said you'd probably be able to tell my views by the end, and I'm assuming you can. For a full list of things I had to cut out, and 2 books I think that every single one of us should read, Machines Who Think by Pamela McCartney, and Artificial Whiteness, Politics and Ideology and Artificial Intelligence by Yard and Katz, and a whole bunch of other stuff that I wish I could like print out and put in every single one of your hands. See this GitHub repo linked at the bottom. These slides are there. They're also in the workshop share folder. Yeah. Thank you for your attention today.
Thank you, Anissa. Any questions from the audience?
Okay. I don't know. I'm just thinking of how to phrase this, but if you can give some thoughts. I've been a little concerned about the conflation of machine learning in general with generative AI and just the use of AI to describe everything sort of together.
Yeah.
And one of the things I've been concerned about is there's been a huge push towards AI from like government funders and like products being offered and stuff like that. And so you can do machine learning research and it helps sell it if you say, oh, this is AI related. But if we end up being like in a little bit of a bubble that's popping, or like some of those products go away, or people have a negative impression of them, it can backfire. If you know, it, like jumping on it because it's a buzzword can also be bad in the long term. I don't know.
Yeah.
I thought I had a question there, but sorry.
Yeah, no, I think I understand the need to maybe use buzzwords in order to get funding, especially when funding might be more political than it has been in the past. I think, however, it's worth having like AI and like, is this a reinforcement model? Is this AI specifically like what machine learning technique you're using? Or is this like generative AI, LLM specific, like DeepSeek or Claude or whatever? I think it's worth being specific, I think is the point that I have come around to. And when I'm not talking about the entire timeline of amorphous AI, I generally too try and specify when I'm talking, and I found that's been helpful.
There's one more question.
Yeah, I mean, this is really thought-provoking and good stuff here. I think, because I find myself thinking of AI as being inevitable, and I really appreciate you pointing out the fact that AI means anything, and that we tend so much to anthropomorphize current AI methods such that we don't really see that it's just a bunch of matrices and statistics behind it. So I think that really helps to clarify my thinking on how I can use AI in my work. So I really appreciate that. And I think that's what you're going for,
It sure
right?
was. That's excellent to hear. Rejecting AI
Limitations.
wherever possible.
Yeah, wherever possible, yeah. So, do you, in your own work, where do you see AI, or the more specific term for AI being important in the work that you are doing?
I think machine learning has merits. I have no beef with machine learning.
Right.
AI specifically, I have used it. I feel like in order to critique something, you have to have tried it. Very similar reasoning to why I read Twilight in middle school. I can't bash it if I haven't read it. Having used these tools, I don't find them personally useful. I know other people have found them personally useful, and I think there's a variety of reasons. And this could be a whole other presentation about that.
Yeah.
But I don't hold a place for generative AI in my future work.
Okay.
I was going to point out that Jeff Hinton started at least some of his work to understand how human brain works. And in that capacity, AI is allowing people to study human brain and brain disorders. So there's no other way to study human brain other than build plausible models. So to that extent, I think there is a fundamental need to pursue this kind of AI. I will not say more. And Ilya Sutskever also thinks somewhat like that, which is biology can think, why can't we make a digital version of it? That's only point. Thanks. Yeah.
Oh yeah, sure. Yeah, I don't know anything about brain biology. I think you would really like, again, I'm gonna plug it again, Machines Who Think. They go through the history of how AI started as like brain modeling and the different like theories of mind that have kind of intertwined with AI. It's really interesting.
Thanks.
Interesting talk, Anissa. I would also add to your reading list Empire of AI by Karen Howell that just came out this year. It's sort of about the history of OpenAI and everything that kind of went into it, and also the effects sort of the LLM revolution is having on people involved and like using it, and like both positive and also a lot of negative. And I think one of the things you're getting at too with this is there, like, ultimately some of the AI hype and push is about power and who has the power, and the AI way of doing it is very, like, there's a lot of built around centralizing power among a few companies that have access to all the infrastructure, but that's not the, like, the AI and machine learning fields in general have not always operated this way. This is kind of a relatively recent change of how things have been done. And so I think it's something we can, like, there's more than one way to do this. There are lots of literature on some of the, like, human-centered AI is one way, or just more like a lot of other traditional ML approaches. You can even use like neural networks and stuff, but in other contexts where you're not as dependent on one framework or architecture or whatever, and it can still be quite useful. But you have to think about, you have to define the problem and think about how you're using it, not just asking ChatGPT how to solve your problem for you.
Yeah, for sure. That's the book currently on my Kindle. I'm enjoying it.
Awesome.
Yeah, thank you. Thanks, Anissa. So the final talk is from Theo. The title of the talk is The Fused Multiply Add and Global Atmospheric Model, an investigation into a surprising correctness scenario.
Hopefully I use this thing correctly.
Did you turn it on?
Yeah.
Green light.
Yeah.
Looks good. from the man behind the curtain. He says, all good. Right on. Thanks for sticking around. I feel like I've heard people make the joke of like, hello, fellow speakers, like when they give the last talk at a conference. But I know some of you gave talks earlier in the workshop, so thanks for, staying with me. And so many interesting talks across such a wide variety of things, many of which, the nice aspect of going last, I get to sort of like build on maybe a little bit. So this is some work done by myself, Theo Price-Broncucia, Allison Baker, Michael Duda, also here at NSF NCAR, and honestly it builds on lots of other work which I'll discuss more too, including like Dorrit Hammerling and others that we've worked with. So it's sort of hard to discuss this topic without first getting into a little bit of a discussion of this concept of consistency testing. I know we've heard like 8 different kinds of testing since the workshop started, and here's like one more. And this basically is an approach developed by Allison and Dorrit and others to try to help address this issue where you have this environment that scientific models are run in, which is constantly evolving, but these models are chaotic. And so you have this internal variability to the outputs of the model, and this difficulty in how you distinguish between differences due to true bugs, or we might just call it unwanted changes, and differences due to chaotic variability. So I've maybe been had to reassess a little bit of my thinking about this based on some of the work we heard about refactoring in E3SM. But in our experience, and I think it's been documented across a fair bit of research, many very innocuous changes can introduce bit for bit level changes to models unless you are very strict about ordering and stuff in your models. And this includes things like changing the compiler, changing the processor you're running on, reordering operations in a mathematically equivalent way. And when you combine this with chaotic dynamics, like you would see in a Lorentz 96 or any other atmospheric model, those really small changes quickly can become big changes, sort of basic chaos. And so we need some way to distinguish meaningfully different outputs from those that are just caused by the internal variability of models. This is the goal of consistency testing and this ultra-fast ensemble consistency test that these folks developed. Basically, the idea is, well, first, let's characterize the output distribution of an accepted configuration, including its chaotic variability, and then we'll actually compare to that. And then sort of extensions of this were basically like, eventually discovered that once you take this approach, you can actually use very short model runs. So even though it's maybe sort of onerous to generate this large ensemble to characterize the distribution, when you use really short model runs, maybe it's not so computationally intensive. This is big work from Dan Milroy. And I'm a little bit of a fill-in speaker here because some people didn't miss, but I'm taking that as permission to reuse some of these GIFs from my PhD defense in May. And so this is Dan Milroy telling Allison and Dorrit how short he was able to make the time steps in roughly 2017. I don't know if I'll be able to ever reuse that again. So it's like my last chance to take it. But basically the approach is when you perturb the initial fields on like a machine epsilon level way, those perturbations will grow in your ensemble. And if you take a slice through that ensemble at some early time step, like 9 time steps for CSM, you can then characterize that distribution. What the ECT does basically then compares new runs and asks this question, how likely was that new run to have fallen within that distribution? Depending on how you define sort of this like bounds of your distribution, you say, oh yeah, we're gonna consider that still acceptable, still within that variability. So that was all sort of like the prequels in Star Wars parlance. Now we've like made it to episode 4, I guess, or something, but then I guess episode 4 came before the prequels. That didn't make any sense. But anyway, so really this FMA stuff starts in 2015 when using the ECT, CSM was hoping to be ported to Mira, and this ECT was used to make sure that the results on Mira, this new cluster, were consistent with like the accepted results on the NCAR machine. And they weren't. So that's the end of the story. No. So that's a little bit of the difficulty of this kind of testing. It sort of just gives you this answer saying these are not consistent. At that point, you don't really know why. So how do you try to figure out why? Well, that became quite, I think, if you asked Allison, maybe a long and onerous journey. But start by looking at the variables that are maybe most different, working with climate scientists to identify code that would impact that set of variables. It seemed like maybe this was related to microphysics code. What impacts the microphysics specifically that would have changed on a new cluster? Like all sorts of things are changing when you move to a new cluster. Eventually, someone suggested FMA. It's probably like months, if not like years of work that is like summarized in this like fun little back and forth chart. And yeah, one more gift. A little bit like searching for a needle in a haystack, right? Because so many things could have changed, and then you're trying to get back to what was the change. And it's like when the change is that you've changed some hardware level optimization option by default, you might feel like you're going slightly insane. So maybe I can actually gloss over this. What is the fuse multiply add a little bit, thanks to the great talk that we just saw on this, the application of this within tensor math. But basically when you need to do a multiplication and an accumulate or an add together, sometimes they call this a fuse multiply accumulate. Basically there have been hardware level optimizations in CPUs, as well as like we heard in GPUs or other accelerators to help you do this, which would usually take 2 steps and 2 rounding operations, doing it more or less in a single step with a single rounding operation. So this is pretty much pervasive in all modern processors, and it promises sort of speed and accuracy improvements. But as this mirror story showed, it basically results in models failing this ensemble consistency test, even when you consider long time averaged output. So I talked about how short you can do these just using 9 time steps. This is a persistent change with CSM. And someone in here can probably tell me if this fact is no longer true, but as far as I know, that FMA is still sort of turned off for these type of models because of this inconsistency. So I don't know what episode of Star Wars we're in right now, but to the present day, basically, and this is probably not totally true when I give this, some of these slides, some of my PhD work had to do with basically updating the ECT to allow it to be more easily used on other models. So it was sort of a little bit handcrafted for CSM and CAM. Initially, there's sort of these like hyperparameters in the testing framework, and we were trying to generalize it somewhat. It's like working with Dorit and Allison and Michael, and we used the model across prediction scales for the atmosphere MPAS-A to do this. And once again, the same FMA issue showed up, that it sort of uniquely caused failures, unique in contrast to all these other sort of common environment changes that might occur, like compilers, core counts, sort of operations. And really, it was like failing this consistency test sort of on the order as if you've like changed a physical parameter in the model by a pretty substantial amount. And I think that's fascinating, but it sort of prompted us to also be like, all right, the time has come. Like, let us find the cause of this thing. And just for context, these are sort of, if you repeat the ECT many, many times and you get sort of an average failure rate, the ECT is somewhat probabilistic, as you know, you're in that distribution. There's some chance even a true consistent output would fall outside of your bounds. And so if you repeat a lot of times, you can sort of get this failure rate. These are sort of the rates of failure we'd expect from other kinds of like numerical environment changes. You change the compiler, you change the core count, you change the compiler optimization level, order of operations. And then, funnily enough, they also changed the default setting when they moved to derecho from Cheyenne, which was hilarious because it gave me a real scare that this was all broken, just like it did for the Mira people all those years ago. So initially, derecho had FMA, I think, on by default. Cheyenne had it off by default, and I was running these MPAS runs, and they're all failing. But again, you turn FMA off to match the previous cluster's configuration, and now we're back to this like sub 1% failure level. So that's sort of like some context. And so how have we sort of gone about investigating, which is really the point of this talk. And so the first thing we did sort of, the ECT, its difficulty is it sort of just gives you this pass failure. And maybe if you run it many times, you get this failure rate, but you don't know that much more about how the failures occur. And some of that's because it uses very few test runs. That's sort of the pitch. It's very cheap to do these tests if you build it into like a continuous integration framework. But once you have this issue, we wanted more information, so we switched to sort of running these full ensembles for both the accepted and sort of the test configuration. And so here is a sample of some of that data. This is for Winfield out of MPass, and this after just 2 time steps. And we have FMA settings and also a compiler setting sort of for comparison. And you see this really strong signal basically from FMA that's like much stronger than the change from changing your compilers. You see 2 things, that we sort of shifted the means of these distributions even after just a couple time steps, but then also that the shape of the distribution is like spread out much more when you turn FMA on. Spooky, weird, I don't know. You see that across basically like all the variables in MPass A. They all spread out faster when you turn on FMA. That's a fascinating thing, and it's like early in the runs. But they also change the means of those distributions. This is that's a little harder to visualize across like all the variables, but this is for like a rain cumulative variable, I believe. And we can see that these basically the trends of the means are drifting apart as the models are run longer for these distributions, depending on your FMA setting. We tried to repeat these like 1-year runs that were done way back in the day for the Mira stuff as well, and we see that this is still sort of a persistent change. It's not like, oh, it just acts weird for 6 time steps and then it all like washes out. You see this like subtle but distinct shift in the distributions of models run with FMA and not with FMA. And for this variable, for instance, is like 42% of the standard deviation of the distribution is like how big the shift is. And it seems that the variables that are like most strongly shifted at a year tend to be the ones that show up really strongly early on too. So that's like another signal that, yeah, it's not sort of just like random difference. And at a year, basically this like failure ratio refers to like how much more frequently are we failing this test than we would expect just if these were sort of like randomly sampled from the same distribution. And we're failing like about 10 times more likely when you switch to FMA. So all that's to say that like it has these unique effects. They're distinct, they're sort of weird, but we sort of want to know why. Again, this is like what we're hunting for. And so we were like digging further and we're looking at the physics parameterizations. We've got these 36 different physics parameterizations to handle subgrid physics. And using the ECT, we basically tested each of them independently for the impact of FMA. This was something that was sort of nice with MPass A. It seemed a little easier for us to basically like change our compiler options by physics module. So we were able to like set one physics module, compile it with FMA on or off, keep the rest of them different. Somebody on an earlier talk was like talking about SEAM and some of this like build system, which is like provides a lot of utility, but it can also be like difficult if you have this like weird edge case sometimes. And MPass was like, maybe we're just like in the make files. Michael was in the make files. I was holding on the rope, you know, sort of like trying not to like get lost in the ocean. But basically, so in this plot, you have the failure rate, sort of like the random failures from the same distribution. That's like GNU if you just change the compiler. We see again, those like doesn't fail that often. You turn FMA on for the whole model versus an accepted ensemble without FMA. You see that failure rate in red there. And then that's like all the physics modules tested independently. That's like the rest of the plot. And you're all scientists, you can probably tell one of these is not like the other. And here it is. It's the 6th class single moment grapple phase microphysics scheme, MPWSM6. It's the culprit. Why though? And that's like a little loose because there are other microphysics schemes that you could switch out. We actually haven't totally tested like if the alternative microphysics schemes show up in this way. But this is a diagram from the paper that described this microphysics scheme. And a couple of like questions one might have is just like, well, does this microphysics scheme for some reason use FMA much more than other physics parameterizations? And it doesn't seem to. FMA is getting invoked in all the physics parameterizations, like roughly similar amounts. It does involve variables with these like crazily different magnitudes. Let me tell you, some people who are really interested in like numerical stability don't like when the numbers look like this. And they really ask you a lot of questions during your PhD defense, and you're like, I didn't write the model, Jay. This is just what it's like. And so this is a case where you might think FMA might be really impactful if you're losing so much to floating point rounding because you have these hugely different magnitudes. Not having to do so much rounding could make a big difference. But again, these kind of variables show up in lots of the physics parameterizations, actually not like that unique. Something that is unique about MPWSM6 is it's like crazily branching. And so basically like every one of these arrows is just a conditional statement that has some, like if else statement. That's probably not like 100% unique to WSM6, but relates to what I'm about to talk about. So basically, then we like ran these code coverage tests to say like, if you run for a short run, like 40 time steps or something, like how much do you get into these different conditional blocks? And basically you get into them a very different amount if you turn on FMA or not. And so if this baseline is just like, how often does it get into these blocks without FMA, you get into them a lot more early in the runs when you turn FMA on. So that's probably related to this spreading out, like you are just getting into these physics blocks that are described in the microphysics more, and there's very few of them, as you see like on the right side, there's like not really blocks you get into equally less or something, sort of like a weird feature. And some of them basically you're running twice as much, like maybe you're getting into the block that says, let's turn some liquid moisture into ice, and you're just like running that block twice as often as you would otherwise. And this is a really distinct aspect of this physics parameterization versus others. So this is like that same plot, but done for like all the different physics parameterizations. And you can see like this is a really unique one in this feature that you might like get into blocks so differently. All right, so now we know that we got these blocks. The blocks are run really differently. I think I'm like right about at the right amount of time. And then I took a big vacation after I did my defense. So this is sort of ongoing work. But basically, we've gotten to the point where it's like, now we know these blocks that are sensitive that you get in and out of. We can look at the assembly code and which lines of code FMA is actually getting used in. So it's like FMA gets invoked for this line and this line. But lots of lines, FMA is not involved. So you actually have this like relatively small search space where we can say like every line in this insane code we can sort of look at and track this sort of path through these conditional statements. And so I don't actually have the answer for you of exactly what lines cause this, but come back next year, or hopefully I will. I think we will in the next couple of months, basically like be able to say like this kind of operation is really sensitive to FMA in these microphysics codes. So that is just sort of like what I was here to present on. But given that, again, it's like the last talk, I think it's like so fascinating, all the stuff that we've heard about in relation to this work. So this microphysics code, I would not, no shade at the people who wrote it originally. They might be in this room, I don't know. But I would not say was designed to be easily testable. So like this main subroutine in the microphysics code is just like 1,300 lines. It includes like all the conditionals are just in the same code, all the maths in that same thing. I've heard from some people at this workshop that it's like good to split this up into smaller functions. Like, I'm not an expert, but all these different forms of testing, I think would be like so applicable here, right? Like there's no unit tests, there's no parameter tests, there's no, the functional testing. I wasn't really familiar with this idea of functional testing, but I think would be so interesting. But I think there is a context to this, like maybe the sensitivity shows up really based on your environment. So like maybe that is sort of this add-on to these other kinds of testing frameworks, which is like, maybe your unit tests need to be run in these many different environments and then maybe compared. I don't know, it's like maybe not for unit tests, that's not as reasonable, but like for functional testing, like are you doing your functional testing with some set of compiler options and then another set of compiler options and ensuring that like both of those still give you consistent results. And to reiterate this aspect of consistency testing, in this case, again, sort of it shows that you can detect these subtle changes that can affect sort of these emergent distribution of outputs, these things where it's like any individual output of these models run with FMA or not FMA look valid, basically. They like both sort of could come from the same distribution. It's only like once you sort of do this consistency testing with an ensemble that you're able to say like, oh no, something on average has changed. Like this, we've like moved our predictions apart, but it can't necessarily tell us like which is the correct answer. It could be that there is some, like maybe we heard, maybe there is some bug that is FMA sort of creates, or maybe FMA is giving us a better answer, a more accurate answer with less rounding, and it is the code without FMA that actually just has like this horrible conditioning, and FMA sort of helps fix that. So consistency testing can't really tell us which of these is correct, but to like rewind up to bullet 2, if with consistency testing you found this sort of subtle emergent difference, I don't know if you call it a bug, if you had all your unit parameter functional tests, I can tell you I would have done a lot less work on this project, but then I would have had to find some other work to like fill out my PhD. So don't test your code. Maybe that's what I should be saying. Like you just like make work for future grad students. I don't know. But anyway, that's all I have to say. Thanks very much. Thanks for coming to the talk.
Any questions from the audience?
Well, I'm going to ask you, this was a fantastic talk, and I really appreciate this because I've been hearing, for years about the problems with FMA, but not heard any of the details. And this was fascinating hearing about it. So thank you very much for taking the time to present this. I'm curious. I mean, you alluded to this in your concluding slide, and I'm just curious if you have intuition about that question of like which is right, because it's like. It sounds like in principle with FMA on should be the better one, but we're always like, oh no, keep FMA off. We don't like what it's doing. So do you have intuition there yet? Should we come back to you in 2 months?
Yeah, I guess we have discussed this a lot, and I feel like maybe, I don't know if Allison feels like her, I feel like we've all had our like money on certain outcomes, that I do think we're gonna hopefully get to like a true answer to that question, at least in this case. Maybe there's other codes that are sensitive in different ways.
Yeah.
There are, have learned a lot more about FMA and the different kinds of operations can be sensitive or not. There are these like summation operations that FMA, basically like you could have tried to account for error in a pre-FMA world. And that would have been good. Like it would have helped you with your bias and like some of these summation operations. But then when you apply FMA to that like sort of bias corrected summation, now it makes that worse than it would have been originally. And so there is potential that FMA is like making this worse. Like this was sort of like code written to not be done. I think my money maybe is that it's poorly conditioned code. FMA is like fixing some of that. Maybe Allison still has her money. I mean, there is like a sensitivity to FMA that like is sort of like maybe not a bug in FMA, but FMA is like causing a bug in the way the code was written, and the code used to be fine. I don't know if I don't want to mischaracterize maybe Allison's thoughts on this, but
yeah, I mean, my original thought was if the code was written well, that if it was compiled with FMA or without, it wouldn't matter. And the fact that it is matter implies it should be written, or the algorithm should have been designed in a different way that wasn't sensitive to this. But
yeah. So I don't know if there is like a total, I think soon, hopefully soon.
I'm excited for the next iteration of the next sequel.
Saw what they did with like episode. When it was good.
We are actually already over time.
Another question, I just want to say we should talk because I have similar issue I'm concerned with.
Yes, please.
Yeah, thanks to you. And we are out of time, so I would encourage people who have questions to contact you, maybe offline or maybe you are here.
Please, now I'm here. I just started this week. So you can come find me.
Thank you so much, and
Sorry.
this concludes this session, and
Yeah, so the next bit I just had allocated to closing remarks. And I don't think we had anything specific. Maybe people are done and want to leave. Maybe people want to discuss things. I don't know. It's up to anybody feel the need to discuss anything, or are we all good? I feel like it's been a good meeting.
More questions.
You can ask Hale more questions. You can go eat more I think there's still brownies out there. You can mix among yourselves. Is that okay with you, Alfred?
Of course.
Yeah.
It's been a long week.
Yeah, we really appreciate everyone coming, and I think this was a great workshop, and I really hope you all fill out the survey that we send out next week. And yeah,
Are the slides gonna be available soon?
the slides are gonna be available and the recordings of the speakers are gonna be available, but give us a couple weeks. Because
Conditional on filling out the survey.
the survey will let you. Yeah, no, just with supercomputing and Thanksgiving break, it'll probably be December before that stuff is over. And like I said, if you missed the one 2 years ago and you're feeling so bad about that, that link to that one is still up, and all the slides and talks are for that. And there's also a technical report that we wrote kind of summarizing things from the last time if you're interested in. So any other?
Are there prospects for future meetings, iterations of this?
Yeah, I mean, to be honest, when we had the one 2 years ago, we thought it was kind of like a one-time deal. We had funding from the UCAR President's Strategic Initiative Fund. But then we got a lot of positive feedback and we thought, what the heck, let's do it again. Alpha was smart enough to get money from the Better Software Fellowship. So, yeah.
Maybe as part of another,
Yeah.
course or something.
I mean, if anyone has suggestions of ways we can get more money for another one, we kind of want to keep the registration fees and everything low, so. And we like to have the food for socialization.
Yeah.
But no, I mean, if there's, when you fill out the survey, if you feel, probably one of the questions will be, would you want to come to another one in 2 years? I'm kind of good with the every other year cadence, give people more time to do crazy things. Any other?
Thank you guys for organizing this.
Yeah.
All right, so we'll just officially end, and if people want to still talk to each other and things, that would be good. Thank you.
Thanks. Okay.